Good afternoon, all the participants. In case you are hearing me well, Ramya, you can just nod. It's okay. So, okay, good. And I'm now sharing my first of all the folder. So, on your screen, you would have. So, first, let me share it. Screen share. Share. Sharing work in progress. Okay. You might be seeing this kind of folder on your computer, correct? Okay. So, as Ramya was explaining to you, today's session mainly I will talk about designing. And I'm not able to see you, so maybe I will be in this kind of mode. Is it okay with you? Yeah. So whole day the setup would be like this. So these are the various Excel files. You must be remembering that there are a couple of slides which I could not complete yesterday. So if today is time permits me, I'll go to those slides. If the time doesn't permit me today, I want to dedicatedly focus today on designing. And I will try to cover as much designs as possible. These Excels are available with you. You can always, refer these Excels on your own. So first and foremost thing, how a water treatment plant is designed, we have to go towards something called mass balance and PFDs. So there are various levels of mass balance and PFDs. The first level of mass balance and PFD, which I'm talking about, is something which you will hear now. This is the sheet I'm opening, mass balance and PFD. Okay, so what you'll see here is something which is an XLS file, which is looking like this. I'll slightly increase the size of this axle, so maybe 120%. And you will find there's a mass balance and PFD of a large ETP plant, which comprises of things like buffer tank, USB, aeration tank, secondary tank, biological treatment plant, etc., etc. So such kind of mass balancing need to be done in any kind of wastewater treatment plant, including sewage treatment plant and all that. And you will talk about certain things called parameters. So here in this particular Excel sheet, we are managing certain parameters. I'll repeat here. We are talking about Q, that is flow rate. We are talking about BOD. We are talking about COD. We are talking about suspended solid, and we are talking about NS3N. Can you see that? So this is something which is a mass balance in a PFD of a project. Now you will have seen something called a blue color line here. Okay, this guy B. So this is basically, it says that there is some iteration issues coming up. How do you correct? In Excel, you always find this kind of issues. So go to File, go to More, okay, and then you go to Options. When the option window will click, you go to the formulas, and it is to enable interactive calculations. And if you press it OK, what is happening is that loop is gone. So this particular project, the mass balancing has been completed. So we have influent, we have modified influent because some waters are coming back from somewhere, right? You also dose some chemicals, like for example, you're dosing poly and maybe NaHCO3. And for poly, if you are using fresh water, so you just put quantity as poly. There is no fresh water, but there's some fresh water being used for, NaHCO3 dosing, the soda ash injection. Okay, so this is the way it goes. Then you talk about buffer tanks, USBs. I'm not going to get into these numbers. Aeration tank, secondary clarifier, biological treatment, filtration, final treated effluent. Suppose some final effluent treated is going. So this final effluent treated is going towards maybe discharge to drain, and you're putting 12 meter cube. Now, if I'm just putting at 12 right now and increasing the size for your better reading, this 12, here there will be something called AA 27 by 24. So typically in these kind of Excel sheets, be careful. Do not try to spoil. First, a little bit understanding you do. So typically where I am entering the data is only these kind of places where I'm entering the data. And balance things, so somewhere there's some formulas, a lot of experience has been built it up, but please enter data only here. That's the point, is showing it. Okay, you come to that. Please enter data only in cell highlighted in green and red, and boxes with the black header do not exist but remain in Excel to avoid duplication. So these are the blocks which are in black, right? Which are black. It does not have the significance, but you do not have to delete it and punch any number. Like for example, something is appearing here now, let it appear. Okay, you don't worry about it. So if we look at this particular Excel sheet, you can find it out even things are going to thickener to sludge mixing to belt press to dehydrated cake. Check the mass balance, 1. Check what you are throwing is 1. Perfect. Liquid wise balance is there. See, there's no thickener, then you can say the Q becomes 0. But don't remove this block. Don't come here and start saying, hey, okay, let me delete this block. So I'm just doing it for you. Suppose I delete everything here, things will become complicated and problematic in my Excels because things are getting linked somewhere. So I'll quickly go to Control Z and leave it as it is. Even if it is not there, don't worry about this equipment. So if some equipments are not there, don't worry about them. Okay, at the right place, put the right number and you will be able to do it the things. So for example, if the same Excel sheet, if you have I do not want about technology and all that. Suppose on the same Excel sheet, you want to go to a flow rate, which is in terms of meter cube per hour, maybe I'll take a 4 MLD plant, 200. So things become automatically a lot of changes. The BOD is very low, maybe 300. And COD is very low, maybe 650. So you must be seeing that certain things are changing in your Excel sheets, right? Then you talk about suspended solid, maybe suspended solid is 145 and ammonia is 10. Is this a designing file? The answer is no. It is not a design file. It is a mass balance file. So forget the mass balance from the design part. There would be some other design files. So input from the design files will have to be built in up here. Now, right now, infrared modified, you have to worry. Tube settler out aeration, you worry. You don't worry about these things. You immediately go to buffer time and start predicting few things. Do you want to think that in buffer tank some BOD reduction will take place? Okay, maybe I can put 1%, 1%, 1% for your knowledge purpose and 1%. I'm just putting it. It is reference is invalid. Okay, it's invalid. I'll go here. It's okay. Why it is happening? Something wrong, gone. I'll just press Control Z. One second, let me see what is the problem. Control Z, Control Z, Control Z, Control Z. Okay, I really don't know what has gone wrong with Excel. So I've just closed the Excel and reload the Excel. You have to patiently wait for me. I know the mistake what I have done. By mistake, I have pressed on this arrow. Okay, so I'm not too sure whether it will correct it automatically. I clicked here. For some reason, my Excel is not performing. That's the mistake I see. Nothing is happening. Okay. I'm not able to close this Excel. Okay. I'm so sorry, guys. I'll go to some new Excel. It's also not working. Okay. That is closed. This is, I believe it is getting closed. Just give me some time patiently.
Meanwhile, those who have not received the Excel sheet, kindly just put it on the question section so we can just email it to you again. All those who have not received the
Any of
email,
you can help me with this? What is happening? हाँ बोल दीजिए. Okay, can anybody confirm whether my Excel is working now? Is my Excel visible?
It's visible.
Am I audible?
Yes.
Okay. Sorry for this interruption. So I'll be careful. I was putting here 200. I was putting here maybe 300 BOD. I am putting here maybe 650 COD. Suspended solids 120, and maybe ammonia. Okay, ammonia of 10. Okay, just for example. So we forget this. In this here I was talking about. So I did mistake somewhere. So I'll be careful of this mistake. Maybe 1% reduction here, one here, one here, and then I click here and press 1. It will take 1. Okay. Earlier I was doing some mistake. So maybe I do not have UASB. Okay, in this particular project. So I just put 0, 0. Got my point? And then I'm directly coming. If you do not have USB or a clarifier, right? Then you can put clarifier only. Maybe if you have only primary. So buffer tank or primary, USB or clarifier. You know, there is options I've given it to you. You may have maximum 2 units before you go to aeration. And when you come to aeration, you may decide that, okay, my aeration is being designed at 3000 MLSS, okay? And my aeration tank volume, which is coming from somewhere else, is maybe 2000 meter cube aeration tank volume is coming. So it says my volumetric loading rate of COD is 1.65, which I know as a designer, it is a wrong design. So I should go for volumetric COD loading of not less than, more than 1. So I'll go for 3000 here. Maybe I refine it as 3200. Till this point clear? You forget this F by MCOD ratio, F by VOD ratio, SRT, HRT. It is all automatically calculated here based on the design what we have done. We do go towards secondary clarifier. Now what secondary clarifier does? Secondary clarifier does removal of the MLSS. And when you remove the MLSS, right, from the secondary clarifier and you get the treated water, then you are eventually reducing some BOD and some COD. So this is what is something which will come from some other design consideration and file. But I'll put that I may get a 90% BOD removal and 85% COD removal from this particular process. And I may go up to say 95%, 90% I'll press suspended solids. So this therefore means is my treated water quality will be BOD 33, COD 98, suspended solid will remain 100 because I have gone only for 90% removal. Now, if I have gone for maybe 95% removal, a better clarifier, my suspended solids level will should have come down, but it has not come down. So you have to tell me, Sanjeev sir, you have done a mistake. So what the mistake I have done is at this particular plant, I press 90, 95. I was not supposed to do that. So I'll do and do Control Z, Control Z, Control Z, Control Z. And what I'm supposed to put is how much BOD I want. So I'll put the BOD how much I want is 30. And how much suspended solids I want. I want suspended solids of 25. That may result in 99% SS removal. So I have to design my clarifier system. Can my clarifier system will be so efficient that I go for 99% or I cannot commit suspended solids 25. Because treated water quality is also important. And ammonical nitrogen here it is 1 or 2, whatever I want to put, I put 2, but it is not very important in this Excel sheet. So what it says, you go towards filtration, you go, this is 30. Okay, this 30 is automatically taken care. This is 30. These are the areas which you can put. So maybe this is 30, you can put 25 here. Okay, I don't mind. So when you put 25 here, something else is happening in the file. Because ultimately, you are committing your treated water quality. You are coming a treated water quality of 230. I don't mind. 91 is by default it is showing. You can go up to this kind of 91 or 95. Now, this is 86%, it is written. So suppose I go towards this as maybe I want to commit only 100 COD. So I can type 100 here. I want to commit 100% COD. I take this particular cell, it is still written as 86. Okay, it is showing here somewhere called COD will be 90. But if I want to put at 72 ppm, right? Just giving example. If I want 72 here, okay, and I cannot go more than 86% efficiency, so I'm in problem. I can't commit 72 because COD by calculation is coming as 90. Please understand, all the calculations are done for COD. Food is COD, not the BOD. BOD is the prediction. Suspended solid number is the prediction. There's no formula by which I will say your treated water suspended solid will be this, your treated water BOD will be this. I repeat, there is no formula for me to predict your treated water BOD. So right formulas are COD. Okay, right formulas are not BOD. So in this Excel, which has been developed, with a lot of pain, please use this. It's a beautiful Excel, but this gives you only mass balance and sizes of the equipment. But what need to actually check by you is further down. Further down, you will go into the sludge area. You would have to predict certain things called sludges and all that, right? So how do that come? So you predict like excess sludge, you have to put here water content in the sludge. Now, how thick is your sludge, right? If you can put 99 here, then you have different flow rate, right? You can see that. You can say, oh, my sludge will have 98% water content, 2% solid content, right? So based on whatever input you are going to give to this Excel, this will behave. And if you keep on understanding this, you will further find that if you are putting in 200 cubic meter of water discharge to drain is 200, right? It is coming here. So water is going in the dehydrated cake as 8. Water coming in, check the mass balance, which is 8, not a problem. These two mass balance should match. 8 should be equal to 8, okay? So this was the first Excel sheet which I wanted to explain. I hope this will be useful to you guys. Any problem, any confusion on this XLS, you can try to sort it out yourself in most of the cases because these are simple mathematical formula. So what my normal request is, whenever I send an Excel sheet to you guys, please save it as in your master folder. Take one copy from there and save it as your initial name or whatever you want to put it, and put a last name, your name or your company's name, and then spoil or use that particular file. If you are in problem, you can always take the master file. So with this, I cross this particular file. I don't save this particular file because I don't know what all mistakes I've gone. And then we move towards our very simple equipment or clarification. So imagine we are trying to design a primary clarifier. How do we design the primary clarifier? We open this Excel sheet, come to the input, increase the size. Any one participant is allowed to unmute the mic. Madam, if you can allow, who can tell me if I am going at a very high speed? Though I have been training people online, so I am aware that the speed at which I am talking and the speed at which the Excel is visible to you, you should be okay. But because there could be some time a lag, I may say something and Excel is not visible because I regularly don't look at my Excel, or sorry, my screen, which is the other screen where I am getting the view the way you are seeing the screen. So if anybody is allowed to
I have
open,
unmuted
unmute
Mr.
throughout the
Doraisamy.
course, organizers, you can take a call on that, and you can keep one person always, interrupting me. Sanjeev, samajh mein nahi aaya, or Sanjeev, you are going too fast, or Sanjeev, can you explain
Yeah,
it
I
better,
have
right?
unmuted Mr.
Somebody like that.
Doraisamy.
So right now, what I see, there should be one Excel in front of you. Sorry?
Hi, sir. Good afternoon. Hi, sir.
Ramya is saying something, but I can't hear.
No, I have unmuted Mr. Doraisamy.
Hi, Ramya.
He wanted a participant.
Hello.
Can you hear me?
Sir, hello. Ma'am.
Yeah.
Good
Can you
afternoon.
hear me? Am I
Yeah,
audible?
I hear you.
I can
So
hear
do
you.
you think
Hello?
Mr. Sanjeev is going too fast?
Yeah. Compare than last 2 days. Today, sir is little bit fast.
Okay.
Because you know the process, and now I'm going into designing Excel, so I'm a little bit fast. So I'll be trying to be a little slower.
Yes, sir. Please. Thank you,
Yeah.
sir.
Okay,
All right.
that's one person remain connected with me. Only one
I am
person.
connected. It's all right. Yeah.
Yeah. And you remain connected with me, and and you can tell me to, you're remaining connected. You cannot tell me whether I am fast. So those who are actually learning the Excel, one of them
No,
should remain.
I felt it too, but then I wanted to confirm it with having another
Okay.
participant.
Okay.
All right.
Okay. I'll go to a little bit show. And so on my screen, now do you have one more visible sheet? Okay. A new sheet is visible. Ramya, you confirm? Because there will be a lot of changes in sheets today.
Yes.
So there is a sheet visible, and right now I'm on a sheet called given input.
Yes.
Okay. So in given input, if you see here, it says mass balance input for a pre-treatment plant, right? Any kind of pre-treatment plant. So what you're going to put into the flash mixer are suspended solids. So just enter here. So I'm entering for you maybe 200 ppm of suspended solids. Got it. Then what is the supernatant for, maybe I can increase a little bit more for comfort of everybody, 800 ppm. Then what is the supernatant from the clarifier? That means what I'm asking, how much water you want from your primary clarifier out. Okay, so maybe this number is say 290 cubic meter, or if somebody wants a bigger number, maybe I can put 1000. We don't mind. And supernatant treated water quality, since it's a preliminary section, I can easily confirm 20, 25, 30 based on our experience. So I just put 30. And now the sludge will start going towards thickener area. Okay, because what the sludge is there, the sludge will go for towards thickener. So let me predict my sludge is only 0.8. So this 0.8 sludge, I have the option of taking into the thickener, or I have an option of I don't have a thickener, I can directly go towards centrifuge. Okay. So if I'm going directly towards centrifuge, because there's a flash mixture, then clarifier, then thickener, then centrifuge. Okay. So if I'm going directly towards maybe centrifuge, then I'll put again here 0.8. That's it. This is important step you remember. If you do not have thickener, that means inlet to thickener 0.8, inlet to centrifuge also 0.8 means thickener does not exist, period. Okay. But if you by mistake you put 1, that means thickener exists. So you remember, because mathematical calculation means they will see only the numbers. You cannot. So if you put 1 here, and if you put maybe 0.7 here, you are doing some big error, right? So that you cannot do that, because otherwise the formulas will get confused. Something will start becoming negative. So if it is 1, it has to be either 1 or more than 1. So let's put 1, and the sludge which you want to throw out may have maybe 80% 70% moisture and 30% solids. So just put 30% solids. So these are the only inputs you have to give in an Excel sheet. So what I'm designing right now, a mass balance for 1000 supernatant clarifier. So when we go to mass balance calculation, the mass balance calculation is already performed. I can easily hide this sheet, right? I can just say hide the sheet. Okay. Can I unhide now? I can unhide now. So this sheet is visible to you. Otherwise, this sheet is not required to be seen by you, because the mass balance calculation, if you see the entire section, is already performed based on the inputs that you have given in the input sheet. If you want to understand each and every cell, you can click the formula and can see from where what is linked. Typically, we have flash mixture, we have clarifier, we have thickener. Now I can show you this in a better sheet called output sheet. So let's go to the output sheet. And what is your plant? This is your plant. Okay, I come to that. This is your plant. You have A water coming, some water coming back from somewhere in the process. So you have B going into the flash mixer. You may add certain chemicals. It's going to the inlet of clarifier. You send X. X is something which is supernatant to the clarifier. From where you go, the sludge is D. You go to sludge pit, you pump it, you go to a sludge thickener. If it does not exist, I have told you how it is bypassed on its own. Then again it goes to the sludge pit, again the pump, then again the centrifuge. And from centrifuge, you throw out the sludge, and the H, which is the centrate of the centrifuge, has to come to a recirculation tank. Similarly, the supernatant of the sludge thickener also has to come to a circulation tank. And in case you do not have anything and you have all the sludge going anywhere, so anyway this loop is going anywhere, right? So if you look at the bottom, the mass balance performance has suggested me for 1000 meter cube water to be produced, my inlet water has to be 1,001.8. Now this is coming why? Because you have a centrifuge. Let me quickly go here and I say, you don't have a centrifuge. So what this becomes? The 30 becomes 1. As simple as that, right? If 30 becomes 1 because you do not have centrifuge, if you check your mass balance calculation, you don't have to do anything in this sheet again. I'm sorry, I'm taking excitement out of the class today because you are saying, sir, you don't have to do anything. And that is what the purpose of tool is. You have understood, you are a good engineer, you understand where water goes, where suspension solvent goes. These are the simple calculation. However, if you want to do it on your own, on a piece of paper, it is cumbersome and it takes time. So what you output you get is, you get this output. 1082 meter cube water has to go in. At the inlet of the flash mixer, the water remains same. At clarifier, this remains same. Sludge to sludge pit goes 82.79. To thickener also 82.79. To sludge pit inlet, all this remains 82.79. Why? Because these units do not exist. Centrifuge, centrate return remains 0. Combined returns also remains 0. Somewhere division 0 is taking place. You have to ignore. This unit is not yours. But you are getting 1000 ppm meter cube water from clarifier. Sorry, 30 ppm suspended solids. Consistency is not important term because we are not dealing sludge here. And total amount of solids in kilogram going along with clarifier will be 30. Whereas there's no supernatant return. The waste discharge wise, if you see, you will have 82 meter cube of water going into the waste. ppm is not important here again. You have a 1% thick sludge, 1% consistency, that will have 836 kilogram of the suspended solids as a dry solid going out. What kind of pressure? Atmospheric pressure is available to you, right? Because there's nothing, right? It's not pressurized thing. Similarly, this also remains atmospheric. What remains pumped, what remains gravity is also written in the bottom. So what exactly you are able to understand? From here, you can make a process flow diagram or a PFD for a water balance of a primary clarification system. And this kind of data, what they will do, they will help you go towards the next level of designing to understand, okay, what kind of pipes and what kind of things we'll have. So these are the equipment which you'll have in the sheet, the fourth sheet, which I am talking about, piping and valve size. Piping and valve size, sorry, it's there. So piping and valve size, which we are talking about, this Excel sheet, I'll go a little bit. So it is talking about line tags, from where to where, right? Inlet before recirculation line, inlet to flash mixer. You know Q, how much water is going to come into this particular lines. Then if you select the round circular diameter pipes, no, I'm not talking about a channel which is rectangular channel. You have a different calculation for that. If you have round pipes, then this is the velocity we are talking about, V. And these are the theoretical diameter which is calculated. So in your project, you should have a 489 mm diameter pipe connecting at the inlet to the flash mixer, right? This line has to be 500. So I'll just type 500 here. This line should be 600 NB. I'm putting 600 NB. This line should become 700 NB. Okay, why? Because flash mixer to clarifier, you can say it's a very low velocity I've considered 0.8, because if it is going in pipe, you cannot get more velocity than this. If you do not want to take a pipe and you want to take a rectangular channel, or you want to just a flash mixer connected in RCC very near to the clarifier, it's okay. Then you forget this velocity and just join the two things. Then water will flow on its own, which is a higher velocity. But if your flash mixer is slightly away from your clariflocculator or HRSCR, then this kind of velocity you have to see. Balancing, you can do these corrections yourself. Maybe I'm just skipping it. Maybe you put 200 and all that. So what this Excel sheet has provided to you? This Excel sheet has provided to you a mass balance, a PFD, and something about the line sizes of various sizes that you are talking about. Okay, thank you very much. I just close the Excel sheets. Okay, now again a question. Was that I was faster on this particular Excel, or I have to slow down further? So then anybody can speak. The next Excel which I'm going to open is now HRSCR design. High rate solid contact clarifier design. So when I'm talking about high rate solid contact clarifier, on your Excel, you might have seen one second. Is it your screen project? Okay, good. So good. So it is a high rate solid contact clarifier. Here I've given some important information. You put the data which you have to design. This is the area of blue, means you have to select something here. How you will select? Based on the process know-how, based on the theory which I have taught you in last 2 days. This is the design data. Typically do not try to change it unless you become a good designer one day, right? Please, you can change this data. I'm there. I always say the rules are there to be broken, right? But for something better rule, okay? So when you become better, then you change it. And this is green, which is your choice. It's a final choice you make. So how much, what was the clarifier which we are trying to make? We are trying to make a clarifier which was 1000 meter cube per hour. So I'll press 1000 here, and suspended solids we were trying to put was 800. So again, I'll put the 2 digit number here. Balance numbers are not here. And then I'll slightly go on the right hand side towards my file. Some kind of
Mr. Sanjeev, participants are requesting you to go down a little slower.
okay, further slow. Okay. Okay, very good. So I'll explain line by line now. So slightly slower flow. Then we have abbreviation here F. Then we put 1000 meter because this is what we took from our design. Suspended solids, we can put 800, okay? Or maybe if you want to change it, you can always put 900. So these are the input numbers for designing. Now this line is called rise rate as per design. Rise rate means the water, Stokes law, and water is rising up, particles are going down, post coagulation, flocculation. So we must predict at what I can rise rate. So there is a guide already provided. You can have treated effluent 1.25 meter cube per hour per meter square, raw water 1.8 to 2.4, up to, depends upon how well you coagulate and flocculate, and take only 1.8 meter cube per hour per meter square if you have to give guarantees related to NTU. Very good quality of water, typically applicable for drinking water segments. So this is the guidance given for rise rate. Similarly, I'll say there's a guidance given for another thing called rise rate. The second one is minimum clariflocculator retention time. How much time the water should remain into the system. And next guideline is for flocculation retention time. So there are 3 guidelines, blue color, it is to be selected. And there is some idea which I have been giving it to you. So now imagine these 2 files, okay. Because if I reduce the size, then some people who are working on smaller computers, they don't see the screen well. So this I'll keep. 130 is the right percentage for me to teach on Excels. Maybe I can hide this particular column, okay? And maybe I can hide this also. But still it won't come near. Okay. Yeah. So imagine we have sewage treatment plants. So as per our guidelines, what should be the guidelines for treated sewage? Whether it should be treated effluent, that is the guideline, or we will follow a guideline of raw water. So my suggestion and experience suggests that primary clarifier in a sewage treatment plant should not be considered as treated effluent. Because when I say treated effluent, I'll talk about secondary clarifiers. So here you can typically consider it is a water, which is a bad water, which has been coagulated and flocculated. So if you do coagulation, flocculation, typically sometimes coagulation may not be required. So you can still go towards a velocity of 1.8. That's the thing which I'll recommend it to you. And minimum clarification retention time. So in clarifloculation retention time, what is the minimum clariflocculator complete retention time? It is anywhere between 90 to 135 minutes. So whatever number is comfortable to you, can just type. I do not mind, maybe 120. Then it comes to the flocculation retention time, 20 to 30, 30 minimum for low TSS and 20 for consistently high TSS. So what we are saying is, if you are always sure that the TSS is higher side, right, which is the typical the case of sewage treatment, then you need not go for 30 minutes, you just keep 20 minutes. 30 minutes is for lower TSS. Now this is the data, height of side water depth, which is called clarifier side water depth. A clarifier has a height, so that is what it is. And then flocculator freeboard, 0.5. These two things are fixed. Again, draft tube retention time means a tube where you will be injecting polymer, etc., where the water will enter first. That area is called a draft tube. And draft tube, typically we keep 1 to 2 minutes of retention only. So we may be pressing again 1 just for making a change. Then these two things again are fixed. Flocculator side water depth, that is 2.2 meter, and height of draft tube, which is typically 2.2 meters. If this is 3.5, okay. So this is the way. The red numbers are the design numbers, which my experience, I am putting it to you. You can give it to the vendor and he'll make the high rate solid contact clarifier for you. Now you see, I have given two inputs. Which one? First one was rise rate. Okay, I'm just coloring it. And the second one was the minimum clariflocculator retention time, which I'm making a different color for this. So these two different criteria will give me two different dimensions. First, they will give diameter based on rise rate. So if diameter based on rise rate, we have to calculate, there will be a lot of areas which I have to calculate. Surface area based on rise rate is 555. Water volume in flocculation zone will come 333. Water volume in the draft tube zone will come 16.67. Therefore, the flocculator diameter will come as 151. Area of draft tube will become 7.58. Total surface area will become 714. Diameter of flocculation zone based on these calculations will become 13.89. Diameter of clariflocculator based on the TSA, okay, surface area will be 30.16, and diameter of draft tube will be 3.11. So typically what it is saying is, I am not very good at making a drawing in XLS, but I'll try to just do it for you once, so that in one sheet you will be able to. Okay, how do you make drawing here? Insert, we have to go towards now. There's something called. I go to home. Shapes. कहाँ जाएंगे? Where I'll get shapes. Okay. Hey, Urmi. Anyway, leave it. What let us understand this is, but there should be somewhere. Sorry? Insert then? Oh, okay. Thank you. Somebody told me insert illustrations. So I go to shapes. So what I'm trying to say is, if this is your draft tube, okay, and then what happens is, again, I have to do this now. So this is your flocculation, okay, and the third one, okay. Now I got speed. Don't worry. Right. This is what I'm talking about. You got the three different diameter. This one will go inside in, and this one will be inside in right here, something like that. So maybe if I have to just show you, this is the way. The three concentric thing will go inside each other. And for all these three things now, you already got the diameter. Okay. This is where 13, 3 smallest, 13, and 30. So this is the diameter of the flocculation zone. So I'm just making it color. What is its significance? How these formulas above, which are there, are come because the height here was 2.2. So when you look at the flocculation tank area, right, if you have to see the numbers, you will find it is related to, if I double click, it is related to this 2.2, okay, and also this 333. So this is the way you can just edit your Excel sheet and understand from where what is linked. So we got 13.89. So this is one condition which we have satisfied. Hang on. This is not the end of the design of high-rate solvent clarifier. Then you also have to satisfy the another condition called diameter based on the retention time, which is A4. So based on retention time, you can calculate F into RT. So F, if you double click, it says E9 into E9 into 16. If I go, I show you what is E9. E9 is the flow rate, okay? And what is the next number? It says E12. E12 is already the minimum clarifier 120 minutes, right? So multiplied by these two, divided by 60, you get the volume. Very simple mathematical calculations. So you get 2000 meter cube is the volume. You are already aware what is the height, 3.5. Similarly, flocculation volume you get. Similarly, draft tube volume you get. Then you understand the total volume is the volume of all the three areas. Then diameter of SCR based on volume. So you have this value of pi, you put it in here, you get the diameter as 29.25. That is where we stop. We do not calculate the diameter of clarification zone or draft tube based on retention time, because retention time has to be certified here as this 29.25. Now, how much is here? 30. And how much is here is 29. Again, I repeat, this one is 30. I'm just making a color. And this one is 29.25. Since you have to satisfy both the condition, you would have to select the higher of the two. So this is the higher of the two as my selection, 30.16. Now, this is what something my XLS program has told me. But come to this first line where I said, what is the final selection? That is in my hand. I am the designer. So if I'm the designer, I go down here. I'll say, okay, if somebody is, I have to give 30 diameter clarifier, I can think of giving 30, but that means I have to do some modification somewhere. I have to probably go for a higher rise rate. I can go to 1.8 and I can ask my colleague or my senior or myself that can I go for 1.85, and senior says 1.85.
Mr. Sanjeev, your voice is breaking.
Okay. Okay. So I try to be slightly slower more, and then maybe, because sometimes the voice breaking is felt by somebody else's poor connection also. So that is what the good thing is. You keep reminding me if any such incident takes place. I'll right now I see internet. My ping is right, 1.85. So I'm saying 1.85. If we put here now and we check back here, it comes as 29.25, 29.85, right? Then I may probably select a diameter of 30. But if because of some consultant, some tender, somewhere it is said the rise rate cannot be more than 1.3. Let me put it. I'm putting that. Sometimes it is only 1.3. You cannot go more than 1.3. I'm just making it bold also for you to be clear. 1.3. This is the condition you have to maintain. And this one you have to maintain as 135. Sorry. 135. These are the two conditions you have to maintain. And put these two numbers. Don't worry, the calculations are being done automatically. And you reach at diameter of 34.38 as the suggested diameter maximum of two methods. First method, rise rate. Second method, retention time. And based on both these things, you have come to 34 dia. So how much you will select? You cannot select less than that. You put 35 dia. So once you already put 35 dia, you go slightly above and check what was the suggested diameter for the flocculation. It was 13.89 and this is 3.11. Here a little bit of engineering optimization may take place. You can take this 35, this one, you go up, suggested is 13.89, you can take 14. This one, you say suggestion is 3.11, you keep only 3, not a problem to me. Because I remember I have taken here to 1 minute. So I cannot go lower than 1 minute. I put 2 minutes here. See, in 2 minutes, if I put, I still remain 35, which is good. I still remain 14, which is good. Now, draft tube suggestion is 4.39. So I make it 4. Now, when I optimize all this at 4 and suggestion here is 4.39, then I can say, okay, let me do this 2 minute as 1.6 minute probably. It is the limit. So when I look at the suggested draft tube is coming 3.93, I provided 4. Suggested draft tube is 13.89, I provided 14. So understand. Then the last one, 35, it is satisfying this one, 30.82, as well as 30.546. So is my design okay? The answer is yes. This design appears okay. Control B, your final design. 35-meter diameter of the clarifier, 40-meter diameter of the flocculation zone. Actual diameter of the draft tube is 4 meters. Some beautiful numbers, right? Because in engineering, you don't want to do 13.29 and things like that. Once you've done this number, you'll ask me, what about height, sir? Height is already fixed to you here. 3.5, 0.5, 2.2, 2.2. So you can prepare an engineering sketch of this particular clarifier and can send it to your civil team to start the calculation for the civil work involved. You can also send it to the manufacturer of the scraper that you please tell me how much is the scraper span width required for this, and he will do calculations for you and he'll suggest you, okay, this is the diameter of the clarifier. I understand. So all these numbers will come to you automatically. Got it? You may not use each and every file. Sometime when in my training, you will not find that. It's, for example, you will say, sir, right now it is missing how much flocculation energy is required. Now, this is not the file where you calculate the flocculation energy. There will be some other place where you will calculate this kind of thing. So as of now, this file was for high rate clarifier. So these are the results which you get. So I'm just highlighting these results for you. These are the results which are the output of this particular file, which you can send it to any vendor, and he will say, okay, I'm understanding what kind of design you are looking for. You can also cross check at times. So actually your retention time is coming 182. Okay, 182 minutes. Now, when it comes to the agitator sizing for flocculation, some people sometimes ask me about something called thumb rules. I will always tell there is nothing called thumb rule, right? So if you want to do the flocculation energy required, right, you have to supply the flocculation zone diameter of 14 meter and height of 2.2 meter to your vendor who makes flocculator for 60 to 70 RPM. Now he will say, sir, this is a typical design of a clarifier. Here you do not require one flocculator. So you decide whether I will put 2 paddles of flocculator, one at each side, or I will put 4 paddle of flocculators in that zone, because it cannot come in the center. Now this is where the design becomes tricky, and we consult always the agitator manufacturing company, giving them our design and also giving them what we call it is the sketch of our clarifier, and then seeking their suggestions whether 2 flocculator paddles are enough or you require 4 flocculation paddles. Getting my point. See, everything has a way to do it. I do not have a thumb rule to tell you, sir, this much flocculator capacity is required here. No, it has to be going to the engineering process person. So this is the file from which we will understand slightly how to design high rate solid contact clarifier. So I'll close the file. I'll save the file maybe. Okay. So what we have understood so far, we have understood a little bit on the mass balance. There's a file called specific water on your computer. Okay. If you are saying this file, you yourself use it. It is required at times when you are doing audit of a ETP or STP. Typically audit of a ETP, you will require this file. So I'm not even opening and closing this file, but just keep it with you. Mass balance you can use, water balance you can use, and HRSCR you can use. Then the next logical choice is that we go for a effluent treatment plant design, understanding this particular design as per typical process which is given by our various manuals. How do you design an activated sludge process? So this I am talking about only CD mode. You understand? Only CD mode means we assume that the nitrogen which is available to us will be removed or reduced by biosynthesis itself. Ratio of COD 100, 5 and 1. So if so it is basically we design for CD mode. So I'll open this particular file. Okay. So when I'm seeing this file, I will show you this table first. So is this table slightly visible to you? So it says characteristics of the design effluent parameter for activated sludge process. And we go slightly up here. And then I say process type can be 3 processes: conventional, complete mix, and extended aeration. The flow regime in these kind of processes are plug flow, complete mix, and complete mix. Usually conventional plug flow systems are difficult to be designed and not designed for a large scale sewage treatment plants. More prevalent ones are complete and complete. And usually the extended aeration is not required for STP. You go only for ETP's extended aeration. So we are today going to focus more. I'll go step by step into this. So what are some key numbers here? I'll go one by one. It is suggested as per the manual of Central Public Health Engineering and Environment, right? CPHU manual isko bolte hain. CHIPO manual bhi bolte hain some people. So this manual suggests that you go for MLSS between 3000 to 4000. For sewage, the MLVSS to MLSS ratio would be around 0.8. F by M should be between 0.3 to 0.5. Hydraulic detention time of 4 to 5 is enough. Theta C, which is the sludge age. Okay, sludge age or that is also known as SRT, whatever you say, is typically 5 to 8. QR by Q should be in between 0.25 to 0.8. That means if you are feeding in 100 meter cube water, the minimum sludge return should be 25%, and you can design up to 80%. I always suggest keep it 100% because you never know when you have to go towards extended aeration. So just keep it with the asset wise, you keep it like this. Then typically the manual suggests if you are going for this kind of data and everything is good, you may expect 85 to 92% BOD removal, and your BOD kilogram oxygen consumed per kg of BOD reduced or removed from the system would be 0.821. Okay, you are allowed in 0.8 also. Now you yourself may question me, Sanjeev, if the BOD is some number, right, in kilogram, how can you give less oxygen? Because the BOD itself says this is the demand. So this demand which we say it is the demand, this demand is evaluated in the laboratory. Whereas in my real size plant, the plant is open to atmosphere. So a lot of free oxygen is already available coming from the environment. And therefore, when it comes to the oxygen to be supplied, this data seems to be okay. You can go even up to 0.8. And 20% oxygen, which is theoretically required because of the BOD testing which you have done as feed BOD, is met by air which is already available in the oxygen. So this design is a pick. So I'm just keeping it in the side. I just keep it here, somewhere here. Okay, I'll just keep it here. And we go to our Excel file. So some areas I've just they were not important, so I've just hidden. So quantity of sewage generated. So maybe we continue to talk about same plant which we're talking about, for which we have designed a primary clarifier. So that we designed for approximately how much? 1000 cubic meter. So 1000 cubic meter per hour becomes a very huge flow rate, right? So 1000 cubic meter per hour becomes how many MLD? Are we good with this? So I put a 24 MLD project right now in front of you to be designed using the guidance which are provided by Central Public Health Engineering Department of India, so that whenever you are bidding or whenever you are putting a tender or whenever you are designing something, if somebody asks you, do you comply to some specification, you will say, yeah, it is in line with the design which has been suggested there. So we move one by one from here. So let's move. I'll reduce something here so that the comment sheet is quite visible. This also is visible. Okay, so we are ready to go. Average sewage flow entering the treatment plant. This is again, the number is average 24 mld plant, right? Assume feed factor of 1. Now, how do you assume the peak factor? So the peak factor would be specified by either a consultant in a tender document, or if you read the CPHU manual, it will say there will be different peak factors, right? The peak factor depends upon city. For a very big city, this peak factor could be only 1.2. Okay. And for a very small plant, this peak factor could be maybe, again, I'm just putting it as high as 2.2. So this peak factor you have to understand yourself. There's no thumb rule for this. So peak factor is something which you will decide here. A 24 mld plant, peak factor of 2.2, no, very bad, very high. It is not. 25 mld plant is typically a plant located for a big municipality. And in my opinion, if I see the manual, 1.2 would be enough. Now you will say you do not have the manual. So manual can be provided by me if you want. I have a draft copy. Otherwise, it is available on the government's website. Just download it from there. It's already available. It is available in the draft form because it is yet to be approved, the latest version. So next we go down to write our some numbers. So maybe we write BOD, COD as 650 and BOD as important. Add soluble BOD only. Because why? Because you already have a clarifier. You have already removed clarifiers. And now we are talking about systems which is going to be designed based on BOD, for which you are going to consume oxygen. So if you have that number, fine. If you do not have that number, fine. Then what right now for calculations I am putting. The right thing is, if all the participants are listening to me well, whenever you take a sample, you take two samples. One you test is as it is. The second you pass it through 0.45 micron paper. Okay, that 0.45 micron paper is the same paper which is used to measurement of silt density index for RO. So that quality of paper if you use, and whatever permeate or product is coming out from there, that you take and send it to the laboratory for testing. Now the COD and BOD value will be soluble COD, soluble BOD. Okay. So if we put BOD soluble here, by which number my entire plant will govern is 220. I'm just putting a number. Then TDS here, it is not important, but I am just putting 1200. ESS, it is important. What is written? Prefer a primary clarifier for suspended solids greater than 75. If not, add BOD load due to suspended solids. So then don't do the SCOD. Then you go towards giving a higher number. So since I already have a primary clarifier, right? So I do not mind, and I just put TSS as maybe 45 or something, because my primary clarifier is functioning well. pH is again a number which has to be put. It is not a number which will, change my design anyway. Good. So having given the input data, now first thing what I have to design is inlet chamber. So can I, with your permission, hide all this thing, because then it will be better visible to you guys. So I'm hiding everything. Okay. So now what you see is the inlet chamber. Inlet chamber, suddenly you say this is the cubic meter per day. The peak flow is 1200 cubic meter per day. In terms of cubic meter per second, all this thing is come up here. If you look here, my peak factor was 1.2. If I reduce my peak factor as just 1, this design is changing. Can you see the inlet chambers design? So it is changing. So the inlet chambers and all those facilities must be designed for the peak loading. So suppose I put here maybe 1.4. So suddenly this becomes 1400. Whereas Average is not changing. Average is this much, but the peak has changed. So this is something which I just wanted you to realize. Here also, once you practice, you will get to know that you are not doing anything wrong. So quality of water is coming 1400 cubic meter per day, which in terms of seconds becomes this. Now we have to assume a detention period. Now how much time we assume the water remains in my inlet chamber? That's the first unit where it comes. So it says 10 to 30 seconds, large to small plant. In a small plant, 30 seconds, and for a large plant, 10 seconds is enough. So let me be very frank with you, 24 MLD is not a small plant. It's quite large plant. Just put 10 seconds. It's enough. Okay? Sorry. Control check. I have put 10 at the wrong place. I have to put only in the green cell. So I come here and I put 10 seconds. And if I put 10 seconds, it says the volume of the inlet chamber requirement is 0.16. Now you have to again assume the depth. When you assume the depth, it says check D35 while entering. Okay. Check D35 while entering data. And we see the check 35. 35 says cross-check flux. And it says 0.2 meter per second. Sedimentation will occur and cleaning will be required. So if you keep the inlet chamber velocity lower than 0.2 meter per second, what will happen? Sedimentation will occur and cleaning will be required. So now let's start. It is going 10 seconds. We are going to enter some data here, and we are going to enter some data here, and we are going to check this. Got it? All four things. So let me enter here as only 0.2. Okay. And this I put 0.1. Okay. Keep understanding. This I put 0.05. Okay. So what it says is, please understand each and every word. What it's saying is, you have a tank of 1.5 meter. You have a tank of 2.25 meter. So the tank size becomes 1.5 meter by 2.25 meter. Okay, till this point clear? And you would have to keep a depth of only this much. If you are not, then sedimentation will occur. So do you want sedimentation to happen in your inlet chamber? The answer is no. Whatever comes here should go further. So by mistake, suppose you put I want to keep the depth as maybe 4 deep water level. No, you can't keep. So your water level here should be 0.05 only. That does not mean you are going to make a tank of 1.5 plus 2.5 plus 0.05. No. You will make a bigger tank. What you will make? You will make inlet chamber which is 2.25 meter into 1.5 meter. 0.05 is the liquid depth, right? And you will add 300 mm above it. One more point. So you will be making this kind of chamber, which will be your inlet chamber. What is inlet chamber? Connect the pipe at one side, take the pipe from another side. That's it. Nothing else. It's an inlet chamber where you are going to give the wastewater. Then after inlet chamber, you have to move towards the screen. So let's move towards the screen. I'm not talking about bar screen. Just put the bar screen. Bar screen will remove coarse bar screen, which will remove only what we call it as a bigger particles. This 20 mm screen kind of thing, a plastic bottle or a cap or a polythene. I'm not talking about that. I'm talking about fine screen which you will put. So what is the peak design velocity? 0.02. Then you say assume clear spacing between bars. Means what is the spacing between two bars? For fine screen, we keep it 6 mm. So there is a 6 mm screen. Velocity ahead of screen. So at what velocity the water should come? very fast or very slow. Very fast means you are having a quick design scheme. Okay. Very slow means you have a conservative scheme. So let me put a slightly more conservative as 0.4. So we require area of the screen channel has come as 0.04. Keep side water depth as 0.4. Side water depth will be as per drain size. Drain size design. Check cell number D30. You're getting me? You are having only this much liquid depth, 0.05, which is moving further, right? So you would have to go back to again design maybe influent chamber. I'm getting my points. So because these are all interlinked things. Right now we are going to just say, okay, whatever you are saying, 0.4 meter per second, I may be going for a vector velocity of maybe 0.5. Okay. So what happens is it should not happen if velocity is too low, that you are not allowed that low velocity because sedimentation is going to occur in the influent chamber itself. So these are some two related things. So I'm just right now putting 0.5 or maybe I'll put 0.9 and we move on further. So keep side water depth here something. So maybe I'll put only 100 mm side water depth. So it says the width of the channel is 0.2. Water depth upstream is 0.1 because this is just a number. It will automatically come. Okay. And then you say T. What is T? It is the thickness of the bar. Okay. Thickness of the flat. If it is 10 mm, then it comes at 0.01. Just T. The number of opening in chambers is coming automatically as 13. Total width of the opening is coming automatically as 0.08. Now you have to put the angle inclination as 55. Somewhere you might be confused. Ki, Sanjeev, are you going fast? Answer is I am not going fast. I am going very slow. Assume detention period in the screen channel. Maybe just put 3 seconds. I do not know. So we get a data call. Length of screen chamber will come as 2.7. Inclined height of the screen H1 is coming 0.12. Velocity to the screen is coming Vs is equal to 1.7 meter per second. Let's just enjoy this data. And it says head loss through screen in normal condition is 0.15 and head loss through screen when it is 50% clog is 0.36. And if you pay the attention in these two numbers, this condition is being met, this condition is not being met. So I could go and change my design. Right now I'm not meeting these conditions, right? And below this also it says should be positive and sufficient. What is this? I'll read now. Water depth downstream. So, after the screen, there should be some water and there should be some depth of that particular water. And the water depth downstream, when it is, so what it is becoming negative. So can you have negative depth? The answer is no. It should be positive as well as sufficient because you have to further do the work. If you understand the plant hydraulics, what I'm talking about, because right now you are in gravity business. Right now you're not pumping anything. So it is one level to another level to another level. It is like water is flowing. So therefore the head works in a wastewater treatment plant, not very complicated, but need proper understanding. For a larger plant, definitely yes. So we will go and try to go and change certain designs upwards. We have reached to a level where I have 130 mm water flowing. Got my point? 130 mm water flowing. Above some level, it should be positive and sufficient. So is it positive? Yes. Is it sufficient? Now my experience says yes. During clock condition, is it positive and sufficient? The answer is yes, positive and sufficient both. But whatever changes I made in my designing, now we further go and check one more thing. Side water depth will be as per drain size design. Check D30. Okay, this is 0.3 meter side water depth. Now I want to keep the side water depth of the screen as 0.3, whereas what this particular sheet is suggesting, if you keep more than 0.05, right? If suppose I want to keep the side water depth as something which I am looking for here. Where is that gone number? I'm so sorry. Yeah, 0.3, 300 mm. If I want to keep 300 mm, right? Always full water coming towards my screen. So can I put 0.3 here? See, I have put 0.3. Now this says you make only a 0.7 meter chamber. Got my point? 0.7 meter chamber by 1 meter chamber, and this becomes 0.08. So I'm in problem. So I'll just check again and put it 1. Again problem, because I have to increase the channel width so that I go towards, but it's still 0.08 is less than 0.2. So that means I'm saying the sedimentation will occur. I'll say, okay, at such a small 0.7 meter by 1 meter, right, is a very small inlet box. Very small. If you can imagine what is 1 meter, it's just my one arm, right? A very small box. And how much water you are talking about giving it? You are talking about giving absolutely almost how much? 24 mld water, which is coming at a very high flow rate, 1200 meter cube per hour. The water may start jetting out of that box itself. So in such situations, my common sense will prevail. I'll say, okay, 10 seconds is too low. Let me go for 25 seconds. When I go to 25 seconds, right, and I have to keep this number as 0.3, I'm in a further problem. I have 1 and 1.5, but this 0.3 number is still giving me a problem. So I'll go for 0.04 only, right, or 0.02. Just try to understand. First you understand, then you will learn. So you'll say 0.02 meter is the only layer which we are talking about. In terms of otherwise sedimentation is going to occur. Okay, water depth flowing is only 0.02, otherwise it is not sweeping, right? The sedimentation will occur. So the next question I'll ask you, okay, what will happen if sedimentation occur? Can sediments come out? No. What will happen? Sediments will push towards the screen? Yes. So no issues. Now I'm telling you first time, you please ignore this. But keep in your design mind then what happens, how it happens, how sedimentation happens. So this you just don't worry. Check 35 entering data, because this you are already modified. You understood, right? Okay, this is the right layer below which actually the sedimentation occurs. But do you bother about sedimentation? The answer is no. So what you will do is, can you provide a screen of 3.7 and 5.5? No, this inlet chamber is too huge. So you will go more towards experience, and you will keep a liquid depth of around 0.4 here or 0.3 here. And at this, you are aware the sedimentation will occur. 1 meter by 1.5 meter screen is okay, right? Got my point? You can even go for maybe liquid depth of maybe 0.2, and you can go towards this kind of screen. Don't go for very big one. This is where what I say is always experience will sometime will be required in construction of the plants. And this is not the end of it. This is just the width of the tank. This is length of the tank. Okay. Now we go further down. At least we have got some more good information here in this area. This is angle inclination. This is all something. Keep the side water depth. Let me see what happens if I keep the more side water depth, maybe 0.4. I'm just trying to tell you how you will become a good designer. So if you keep a higher side water depth in the screen of 0.4, you are very good here in the downstream equipment, 0.35, 0.30. But it is too much, right? It is too higher than the sufficient one. So I'll go back and no, I keep a liquid depth only of 0.3. Because higher the depth you keep here, higher is the chances of settlement in the influent. Because why you are keeping these two depths? You are keeping these two depths separate because the water does not change the level. water remains the same level. Suppose if there is no screen, so there is no difference between inlet chamber or the screen chamber. Both are the same thing because water will remain at same level. And if you are putting a screen and it is putting too much of pressure, the water level may go up in the inlet chamber. So that you have to be avoided. Whatever coming must go through the screen quickly and run away. So if you look at this particular design now, so this one depends opaque, positive and sufficient, and we therefore provide a screen chamber with a screen of 1.2 meter, where it is a 0.2 meter, 200 meter is the liquid depth which we are talking about, 0.3 meter is the side water depth, okay, and we also are talking about, you know, 0.3 meter of freeboard on the screen top. So we will provide a 1.2 meter long chamber just to provide a fine screen, and water will go out of it of 200 mm thickness. Now, if you don't want to do that, if this 0.2 which you are talking about, now if you look at this particular number, width of the each screen channel, which is coming from 42 and 43. If you look at the 42, this is 42, and if it is 43, it is a side water depth. So if I want to change this 0.2, so I can go towards this as 0.2 here. Be 42 divided by 43 and round it to 2. Okay. Okay, 42 and 43. So if I'm trying to reduce this, I am going towards a screen like this, 1.2 meter by 0.5 meter, 0.8 meter, 0.005. But what we are saying is this is not coming as positive and this is not sufficient also. Okay, so the both are coming as negative. We will go above again here and we'll keep again this thing as slightly more, 0.08. So this tells you that again, this becomes positive and sufficient, but during clogging, it is not becoming positive and sufficient. So maybe this I'll go towards 0.1. And at this number, if we hold on, we say 1.2 meter box, 0.4 meter of the thickness of the screen, 0.1 meter side water depth. This is positive. This is still not positive. So what happens is, it's not necessary that every time I have to make it positive. I'll make it positive somehow for you. I'll go toward this as 0.12. So I'm still in negative here. I was sorry, I was pressing the wrong of this thing. So again, this 0.12, I just make 0.15. So if I look at this keep side water depth as 0.15, this is the final number. If I agree with my plant, then for all other formulas which are fixed, I am positive and sufficient. I'm just trying to become a little bit positive. But when I look at my drain size, it says 1.2 meter by 0.3 with this much. Now at this thing, if I have to realize, what is, let me go back and check up what is the velocity I'm talking about in my screen. The velocity ahead of the screen is still quite low, right? 0.4. But if I would go for a lower velocity, maybe 0.3, which I would prefer finally, low velocity, because even one velocity, is 24 mld is a medium flow. It's not a very high flow. Their flow could be even 100 mld, 120 mld, that kind of levels. So these files are, designed for all kind of flows. So here, when I say, okay, I'm getting a sufficient width of the screen also. You can see 400 mm ki screen आई. Otherwise, the width of the channel where the screen was getting fixed was very, very small. So now my experience suggests typically 1 meter by 0.4 meter with 0.515 meter SWD and 0.3 meter freeboard appears to be a nice screen chamber. It takes a little time. I took 25 years. So if you feel that I'm going fast, it is natural. Sometimes I go fast. It will take time for you to really go through each and every number and understand these calculations. But finally, right now, I am appearing a little bit more satisfied with my design. Actually, I provided chamber of 1 meter by 0.5. No, I'll put half meter chamber, right? And what I'll do is the screen I'll put 400 only. Okay, maybe with a little bit of RCC construction, because 400 mm is very small width. Still I'll try to keep more relaxed. So there are three things we have to do together, gentlemen. Sometimes we feel ki Sanjeev will provide that Excel tool, and we'll put some data in the Excel tool, and we'll take a printout of a PNI diagram, layout, and construction drawing. It will happen one day, but not today. There will be some experience required here. I still feel that 24 mld plant, this size is small. I would go for a bigger screen chamber, because theoretical calculations or calculations which are based on theories and all those things are important. That's why these tools. But they are the only things by which you should design. The answer is no. Some experience will come into the picture. If you design this, is it sufficient? The answer is yes. It will work. It will perform. But is it the best thing? The answer is no. Yeah, you could have been more relaxed in terms of designing. And after all, very important thing I always say, always be a little more relaxed in designing when the cost is not too high. So when you want to optimize things, you optimize in opportunities will be there in aeration tank, opportunity will be there in the primary clarifiers to optimize things. Here, these things do not cost too much, like grid chamber, screen chamber, etc., etc. So make it slightly bigger, even if they are not required theoretically. Okay. So can we request everyone to take a break for maybe 10 minutes? Okay, 15 minutes. Ma'am, can I request for a 15-minute break?
Yeah, okay.
Okay. So it is 4:26 in my watch. So let's try to meet after 4 minutes. That's 4:30, 4:40. Bye-bye, everybody. 4:40.
Okay. Meanwhile, I would just like to inform the attendees that we have another free training session on yet another topic called Industry 4.0 for water or wastewater treatment with IoT, AI, and ML. That would be Internet of Things, Artificial Intelligence, and Machine Learning. So we have this free training session on Saturday, that is the 14th of August, from 3:30 p.m. onwards to 5:30 p.m. So this is a free session. Kindly look out for your emails. We shall send you the registration links for the same, so you can register and also take benefits of attending that free training program. Thank you.
Hello, good afternoon, everyone. Am I audible now? Are you back here?
Yes, Mr. Sanjeev.
Okay. So, participants, during the break, I got a phone call for some of the participants. One participant knows me personally. He has been working with me for quite some years. So he gave me a feedback that Sanjeev, the Excel is going very nice, but probably it is a little high-fi for some of the people. So can you give a start with some simpler, thing, because we do not work such a high level 24 MLD and all that kind of project. हम छोटे छोटे प्लांट करते हैं, तो कोई छोटे प्लांट की सिंपल एसएमएस कर सकते हो तो अच्छा रहेगा. Something simpler, right? I'm sorry, I started speaking Hindi. So I'm just holding that Excel right now, and I've put a new Excel which is with me only right now, not with you guys. So I will be showing that Excel to you first, and Ramya will email that Excel to you shortly, because I just discovered that simpler, Excel. So if you see my screen, it is visible to you. It is called Impact ASP, advanced, as per CPHEEO manual, right? This is the file which you guys do not have. So this file I'm opening right now. Right now you don't have this file, but it is simpler. You will be having less complication here to learn. So you learn from here, and then we go back to that slide. Same file. I'm just repeating. You can see on your screen, you would have seen same thing, right? Just keep it in the side. So let's design a 1 MLD plant and forget this column winter. You'll get more confused. So let me try to reduce things. So we want to design a 1 MLD plant. Just to change the data, I'm making it 1.1 MLD. And next, you can read yourself on the screen now rather than co-practicing with me. So maybe you are above sea level. What is the significance of this? The air has got oxygen, and oxygen is dependent upon how far you are from the sea. Like in Himalayas, you have less oxygen. In Mumbai, you have more oxygen. So I'm putting maybe 450. And we are talking about temperatures, because temperatures are also important for understanding the transfer of oxygen to DO. So I'm putting a temperature of maybe 25 degrees centigrade, ambient temperature. Now, the simple word is primary clarifier affluent BOD. If you have a primary clarifier, after that, whatever BOD is coming to you, you put that number. So I'm right now putting a number called 235. So input is given. Okay. Then sometime if you have a thickener, from the thickener, the water will come back to you. Okay. Thickener for overflow return as a fraction of the plant flow. So from my experience, I am putting as some fractions, right? So maybe I'm just putting only 0.1%. Oh, sorry, as a fraction, right? So fraction is 0.1. Okay, something. So 0.11 MLD additional water is coming at the inlet because of this, and thickener overflow is centrate. Maybe I can put again from centrate. I may be putting some water as 0.1. I'm just putting a number for, because this you'll find out from the mass balance file, right? I showed you the mass balance file, so I'm just putting 0.1 here, and maybe I'll just put 0.05 here. So to that extent, this much, and when you are having this particular water, you put it with this particular number. Balance things just remain. Centrate from sludge dewatering as fraction of plant flow, leave it like this. Centrate from sludge dewatering return becomes 0.11 MLD. Centrate from the sludge dewatering return to return BOD, whether BOD is higher or lower. Okay, if you have to, because some suspended solids come, right? So this we have to predict how much number. Typically, my experience suggests this number, as it is, what is written here, 500 and 380 are good enough. And just keep these numbers. This is experience. Everything may not be possible for me to explain. Now, influent BOD to aeration therefore is coming as 259.13 milligram per liter as the accumulation of all these things. Primary is 235, but because some sludge is returning, etc., to the aeration tank, you are going to send a BOD which is 259. And after clarifier, you want the BOD to go out as 20. Okay, just 20. So I'm putting the number, I want 20 or 25. So let me change this number as 25. Now what happens is, weighted BOD to be removed in the aeration tank therefore is approximately this much ppm. Okay, BOD removed is not the right word. The right word is COD removed, but it's okay. This is the simple way you want to learn. So simple design is BOD. So 234 point this much. Now there are so many criteria which were given here. Okay, you have to maintain MLSS, you have to maintain F by M, you have to maintain HRT, you have to maintain theta C, etc. So let's evaluate how we do that. So assume, I'm using the word assume, which I never do. So I'm asking right now to assume that you want to do a complete mixed reactor. So your MLSS level should be 3000 to 4000. So I'll put maybe 3200. And you have to have put F by M in between 0.3 to 0.5. So I'm putting 0.32. Yesterday when I was talking about if you fix these two things, something else will be fixed. Authority is already fixed actually. Okay, so let's evaluate for this much MLSS. Okay, F by M ratio. If I select, how much is the food? The food is automatically fixed. Mass is automatically fixed, and therefore the aeration tank required. Okay, aeration tank volume required as per F by M ratio is fixed as 289.23 cubic meter. Can I click it red cell here? Okay. And can I make it black and red? Let me make black and red. So now this is one number which you achieve. The second condition is I want to understand mean cell residence time. There's a theta C. Let me put it only 1 and see what happens. So based on 1, I have a yield of my biomass, which is Y. I have depth of my biomass, which is KD. So based on the aeration tank calculation, it says aeration tank volume based on MCRT is 37.96. So therefore, there is no point, because I have to keep on increasing this number till it becomes 289, because this 289 number will satisfy these two conditions of design. So I type 10, I remain to 51, I go to 12, I go 280, I go 13, it becomes 293. Wow. Okay. So approximately 12.5. Let's lock it at 12.5. 287, 289, we are almost getting close numbers. We move further down. Then we have to maintain the third condition from HRT. Come back here. It says your design should have hydraulic time of what was 5 to 8 days, right? If you are following extended aeration, which you are not following in sewage, you can. It's not that I'm not saying you cannot. You can, but most of the time in Indian context, you may not have to go towards extended aeration. So if you are going for 5 to 8 hours of theta C, okay, you've already gone to 12.5 theta C because of some other criteria. Cut off point. So you cannot design complete mix. You have to go towards extended aeration. Hope this word is clear to me. You have gone for first design of MLSS, and F by M, okay? Because of which whatever you got, you have seen the theta C has already become 12.5. So it is not that you have to decide today it is extended aeration or today is complete mix. If the theta C is going up, you are already working in the extended aeration. So in extended aeration, it says you should go for 12 to 24 hours of HRT. And you should have a food to mass ratio of 0.1 to 0.18. And MLSS could be between 3000 and 3000. So 0.35 loading, right? If you are doing, you are going towards theta C, which is exceeding, So let me go it back and try to put something called only HRT. Now the third thing, HRT. Let me put only the maximum HRT which was allowed was 8. So what happens? At 8 HRT itself, okay, which were my complete mixed reactor design, my volume has become how much? 366.67. So aeration tank volume based on HRT, how much is coming is? Okay. So now I go back here and I say, okay, let me reduce the food to 3000. Let me keep it as 0.3. So I am 329. But unfortunately, the theta C is going up. So your 329, 366, right? If I have to give 366 because 8 hours is the complete mix time, 8 hours maximum. So maybe I can go towards just I to 7. At 7, I get 320. But here we have come at the bottom of the table. Which one? 3000 and 0.3. Can I go below that? The answer is no. So 3000 and 0.3 are the two numbers which are already fixed. I cannot go below that. Therefore, 329 is something which I cannot go below 329 if it is complete mix. 320 is the number which is coming from 7th, which is okay. So at this time, my SRT is automatically coming more than 12.5 and I have to ignore it. Higher SRT means something else, higher oxygen consumption and all that, that will take care. It is not having that bad effect. We can put it 13 as it is, just put 13. So there are 3 conditions to be satisfied, 1, 2, and 3. So all the 3 conditions, if I've satisfied, I require a volume, which is now I can make it final green and 1. This is the design which I'll follow, 329.08. So you cannot reply back to me because it's a monologue. This is my maximum of 3 volumes of aeration tank. So what I have fixed is my aeration tank. Nothing great has to be done. For 1 MLD plant was this, 150 MLD, plus 50, nothing has to be done. The plant design is still the same. Aeration tank volume requirement is this. This requirement is this. This requirement is this. This is the final design. You required a 15,000 cubic meter of aeration tank. So it's a very simple process. The aeration tank we straightforward reach. Let me go back and put only 1.5 MLD. Let's not do a big design. So imagine we have an aeration tank which is 329 meter cube. Now what is the next thing? What you'll do? You already fixed MLSS. You already fixed F by M. Your SRT is known to you. You already got the volume of the aeration tank. Now, when you have the volume of aeration tank and we also have the concentration of MLSS and also MLSS to MLVSS ratio is assumed as 0.8, you are aware about the amount of bucks which are available to you. You also are clear how much of kg oxygen now you want to give for BOD removal. What the manual says, you can give 0.8 to 1.0. So this is 0.9. How much you want me to give? If you want more air to be given, let us put 1. And if you want less to be given, let us put 0.8. All the numbers are okay. There is no problem. So let us put 1. Okay. We put the 1. So we have fixed the oxygen needed per day is 296 kilogram. And the residual DO in aeration is 2. This much I have to maintain. Okay. These 2 numbers, this is fixed. So now I have the next choice. Shall I use surface aerators or shall I use diffusers? So let us understand what is the surface aerators. If you want to use surface aerators, you have to read the CPHU manual, clause number 5.8.7.5.3. That will give you value. Similarly, this, if you have to see this value is typically 0.8 to 0.5. See, there is no end to learning. You think something will be thumb rule, then it is impossible to have thumb rules. Right? Well, thumb rule based plants don't work. Alpha value is this, which is a typical value for a surface aerator. Beta value is 0.95, which will come for 5.8.1.7.3. DO at the operating temperature now is automatically calculated. This is the formula above written. See, how do you calculate the DO at this operating temperature? 8.22. DO at the operating level, 7.81. All these numbers will come. Oxygen tension, milligram per liter, automatically will come. It's called milligram per liter. Oxygen gradient, it will automatically come 0.59. Just leave these numbers. Enjoy the training. Temperature difference is 5, which is C6 minus 20. What is C6? C6 is the temperature which we have kept. Okay, you understand? C6 is the temperature what we have kept is here. This is the significance of temperature. If I put 30, it will be 30 minus 20. What is 20? 20 is the international accepted ambient temperature. Indian temperature is 25. But all the engineerings have to be done on certain international standards. This is the Canadian number, 20. Most of the time, most of the work done in India, most of our manuals, I'm sorry to say, but are the copy paste of that. So Canadian manual has 20. So our Indian manual also has C6 minus 20. Okay. So otherwise, I can also do all the formulas and all the calculation on 25 also. Then I don't have to do this factor. But I have to do it because I am following those Canadian guidelines to start with for all these surface aerators. Come here. So we got this number as 5. Temperature coefficient, therefore, is 1.03. These are the numbers. You just put it. Don't ask me from where they have come. Temperature correction factor is the power of C to C43 to the power C42. What is 43? 43 is coefficient, temperature coefficient. What is 42? Is the temperature difference. So this factor comes as temperature correction factor. It comes as 1.16. Conversion factor to the standard condition is 0.57. And oxygen needed under standard condition therefore becomes 521.17 kilograms. Oxygen needed for this particular design is 521 kilogram. Now let us look at this. Typically 10 to 15% you provide factor for safety for intangibles. So therefore you require how much oxygen? 573.28 kilo. Now when you go and start buying the surface aerators, those surface aerators vendor will give you only this data. You ask them, how much is your oxygen transfer capacity of the aeration you are talking about? So they'll say, sir, typically 1 kilowatt per hour kind of aerator will give us 1.8, 1.2, 1.3, 1.4. If anybody says more than 2.4, superb. I don't think it is possible. Anything saying less than 1.2, it's a problem. So you have to buy the surface aerator from the vendor. These are the engineering numbers. It is not that everybody has got the same surface aerators. Some good companies have the better ones. Their designs are different. So it's a totally engineering subject. So what number you have to put, I do not know. You have to talk to the surface vendor and ask for test certificate. Okay, you prove your test. So they'll show you some kind of test certificates also. The way in pump we have a characteristic curves. Similarly, in the surface aerators also we have some curves and some proofs. Our surface aerator can give. So let me put a number called 1.6 here. Since long it's 1.8 ever since I made this file. So 1.6. So kilowatt of aerator required is 14.93. So two things you have fixed, gentlemen. Please understand. One, aeration tank size. You have already fixed. And kilowatt of aerator, you already fixed as 15 kilowatt. Now, when you start going towards the hydraulics of the plant, you might have to construct this particular tank. Okay. The 329 cubic meter tank, if I assume that the depth at which the surface aerator is functioning is maximum 5, then I'm just writing a formula here equal to 329 divided by 5. So I get the size area of the aeration tank. So it is possible in this particular design, I might say that 65 area. Suppose I divide it by 15. So I divide it by 15. So how much it becomes? 4.38. Okay. Are you getting it? So it is possible I might say कि make 5 meter cube by 15, 15 into 5 into 5. So 15 is one dimension, 5 is one dimension, right? So I make a 15 by 5 tank. Can I make 15 and 5 become 75? Understand? So if I make a tank which is 15 by 5 and each surface aerator gives me efficiency of oxygen transfer in an area of 5 by 5. So I have 3 blocks, 5 by 5, 5 by 5, 5 by 5. 3 surface aerator. Each rated for how much capacity? 5 kilowatt, 5 kilowatt, 5 kilowatt. 15 kilowatt energy given. Aeration tank sizing becomes 15 meter by 5 meter. Are we understanding what I'm talking? So it is never that one file will give you one design. But this design, if I'm going to do it for you, you have designed it aeration tank nicely. Now you may say, sir, scrap it. I don't want to use surface aerator. So don't use, no problems. I'm just trying to tell you that if you use surface aerator, remember this number, you'll require 14.83 kilowatt of energy in this design. Now you say, I want to use diffuse aeration. So then again, don't ask me these numbers. You have to read a lot yourself. Factor for temperature power 3, factor for temperature power 2, factor for temperature power 1, density of air or operating temperature 1.2, 0.8, automatically it is coming. You can see 1.2285 plus C53 minus C54 minus C55. What is these numbers? Just go back. Sorry. Just go back and just click here. So you can see it depends upon so many factors. So this is 1.22. This we all know. It's a universal value. Some may find a different figure with the vague reasons. Okay, but you just say content of oxygen is 0.23. You accept it. If you don't like it, I don't mind you putting 22. Now, some people may say, no, this is 22, 21, 23. This book is 21, 23. This number is arguable number. How much is the oxygen in here? So 0.22. Okay. Some people give a very different logic. So, no, this is a polluted city, Delhi. So, shall we keep it 0.21? No, it is not that much. Okay. So, this is an argument which people say. I say 0.23, which is written in our 9th class chemistry book. Please follow that. You don't have to change this number. Then, oxygen needed for residual DO per day is 2.2 kilogram per day. And total oxygen needed per day is 298. From where these numbers have come? These numbers have come from the above design which you have done for BODs, right? These are the numbers. You can see that. 296 plus 2 is equal to 298. This number is already come here. Okay. So air needed in cubic meter per day, therefore, will become 1059.24 cubic meter per day. Then we talk about transfer efficiency of the diffuser per meter of depth. Then we talk about something called transfer efficiency at the design depth, therefore is 0.28. Why? Because we have a design depth. Where at C29 we have to fill how much is our design depth. Where is 29? We go here. See, liquid depth. Restrict to a maximum of 6.5 meter if air is cool. If air is not cool, then you restrict it to only 5.5 because hot air may not travel that much. Okay, so this is the liquid depth which we want to keep in the aeration tank. So this number I was there, transfer efficiency of the liquid depth, it comes 0.28. Then again, diffuser fouling factor. You have to check it with the vendor. What is your fouling factor we consider, right? So maybe it could be 0.03. Somebody's diffuser is very good. Somebody's diffuser is not very good. Then he'll say, okay, consider 0.05. And diffuser lifetime cycle. How much time you want to change your diffuser? Somebody may say 3. Somebody may say, don't want to change the diffuser for 7 years. Of course, it is a problem. Diffuser don't last for 7 years. Okay, you may write it, but the real thing is typically every 3rd year the diffuser need to be changed. So press 3. So this 0.5 and this 3 becomes 1.15. Then provide factor of safety for intangible becomes 1.1. Okay. Therefore, the air needed for oxygenation in cubic meter per day will come as 3851.77. And air needed for oxygenation in cubic meter per hour is simply divided by 24. This divided by 24, you get 160. Hang on. So you require this much of air. Still, I have not solved the problem. 160.49. We remember one number, which was 14.93 energy required. Up to here, we already know one number, 160.49. This thing. At this point, this is what I was telling yesterday, surface aerators versus the diffuser aerators. When you want to make a calculation, what you have to do, you have to understand the air has to do also something called complete mix. So what is the criteria to check whether the air is mixing well or not? So this is the criteria. Air mixing criteria says per cubic meter per minute in a 1000 cubic meter tank should be 16. 16 cubic meter air per minute per 1000 cubic meter tank. Okay, this is the criteria, 16. So therefore, air needed as per mixing, as per manual. Which manual? This is what the manual I'm talking about. Central Public Health Engineering Manual. His requirement is 315. Though your air required for oxygenation, theoretically, is only how much? 160. But for mixing, you need air. So how much is that? No voice? What? No. Okay. So I hope everybody is listening. There was no disturbance. So air needed for mixing as per manual is 315, right? Now, will you give the double the air which is required? Look back again. Next criteria is air needed for mixing cubic meter per hour per meter square of aeration surface. And this is 2.7. From where it comes? It comes from 1.8 to 2.7 as per US EPA, 6225 88501, page number 38. So there's the US EPA guidelines with respect to how much air is enough for mixing, which is different than the CPHU guidelines. CPHU guidelines, again, I'm telling you, I want to repeat that word. Don't mind that. It looks like copy paste of Canadian manual, nothing else. So Canada and America, there's some difference. So this is the EPA guideline, Environment Protection Agency of US. So their guidelines is as long as you are having 2.7 meter cube per hour per meter square of air, that is sufficient. So our surface area of tank is 59. Not the calculated one which I was telling 15 by 5. The actual one where I said this is the volume and this much is the liquid depth, from where it is come as 59.83 meter cube. So air needed for mixing of as per US EPA guidelines is 161.55. Got my mind? Therefore, maximum of this air need is how much? Is actually our Indian guidelines CPHU manual. I do not know why it is, but if you ask me technically, SSR is okay with it. If you are giving this much of oxygen, done, sign off. Because it is meeting a EPA regulation, whatever criteria they have said, because they say that their right point is also right. They say that turbulence in the aeration tank is not important. The important is that each and every place is really shaken nicely, a little bit shaking. And for that, the right criteria is how much air is coming out of the surface from top, right? And that therefore, I sometimes follow this. I ignore this. As long as this one is greater than this, now I accept this criteria. Simple. Okay, move further. Minimum, maximum air. Suppose I take this. If suppose somebody says no, you have to design the plant as per CPHEEO manual only. I don't want to listen to anything. Please design as per this. So my design becomes this one, red and white. I just do it. Okay. So this is the air requirement, but we do not have to just stop it at this time. So air needed as per higher of the oxygenation and mixing is again 315. Now, what is this called air needed for test standard versus test conditions? See, all these equipments, right? Typically, air diffuser, these, that, whatever number they present to you is based on the, their test conditions. So there is a variation between what exactly it is. And let us go to this factor C75 and C45. And what we find in C45 written, you can see that conversion factor for standard condition is 0.57. Okay, this is what comes from so many knowledge things. So if I start going into the air requirement, an apple to apple comparison of these two processes, one is surface aerator versus the another one is the diffused aeration, I'll require actually this much air. And if I actually require this much air, 551.8, this much, friction and other losses will account for something which is 0.2. This is designer data. Typically, you have to put this. You don't sacrifice on this. And liquid depth as per water column of air pressure is around 6.6 liquid depth, right? This 6.6 has come as C29 into 1 plus C77. So 1 is what? 1 is added for in C77. C77 is our this fraction, 0.2. Okay, so 0.2, so 20% extra. Typically, we are talking about. So you require kilowatt of air needed from air compressor, which is a 1400 RPM compressor, as 24.3 kilowatt. Okay, these are again the theoretical calculations. So this you please BHP is equal to 0.03 and all that. This you again cross check with your vendor. So what exactly this file is telling? Don't use air blowers in sewage treatment plants. Use surface aerators because they will give you more energy efficiency. 15 kilowatt work is done. Okay. Bio-oxidation requirement is fine. You can see that it's only very low. It's only very low. But because you have to keep it is as a complete mixed reactor, it is suggested you give this much air. And that's where the problem comes. Sometimes if you do not think and you think only 315 air is given, not 555, and that too you don't increase by 20%, so you'll end up this much air. So imagine if I just say this one is equal to, I'm just putting this number, equal to only this. So it's still 20%. You say, no, I don't want to give 0. Okay, so you require only this much, right? Or even if I say, no, whatever is the bio-oxidation requirement, 161, that much only I will give. So this number becomes equal to this number. So still I am 15.55 kilowatt, right? Whereas surface aerator is giving me 14.93. So in any condition, if you talk about, typically surface aerators are much more efficient equipments. But what happens is when the flow rates are very small, now same plant of 1.1 MLD, let me just put a quick number and I say, no, I have only a very small 250 KLD plant. At 250 KLD plant, when you go and start buying a surface aerator, you are in problem. Understand? You require a 4 kilowatt surface aerator, and people feel, who will get into all these issues? And let us try to put the diffusers. Okay, because diffuser wise, if you say, it's never energy efficient, but you would have to put this much of energy which is required. Okay, and that too here, the mixing criteria is superseding of CPHU 71. If you go for the US EPA guidelines, you could have given this equal to 36. That's it. Go for it. And why it didn't change? Okay, it didn't change because anyway I checked it with 36.7. So control check, no problem. Okay, if I would do it as per the mixing criteria of CPHU manual, I'm in problem. Because surface aerators are efficient equipments, but you do not want to buy surface aerators because such a small flow rates and all those things. You have a hassle in buying it and installing it and all that. So then therefore people prefer for this. So I will stop on this particular file here because after that there are some things which are written as called sludge flow and all that, which will appear to be complicated to you. Something called YOBS. So immediately you'll say, what is Y and why I have not taught you what is Y and what is YOBS. So I'll stop the file here only. Okay, this one file. There is a lot of good things about this file, which I'll send it to you. It will calculate even access return sludge to, your all this thing. So I'm just closing this file right now here. But this design is always a very good design. Okay. Is this screen visible now? Okay. Good. So we will have just finished the screen design. Something similar way, you have exactly the grid removal unit to be designed. All these numbers you have to provide. You require typically 2 grid. Why grid channel? Because one is in working, one is into cleaning. So you require typically 2 grids. This appears 0, but it is not 0 because it is 1 to the power 0.1 into 10 to the power minus 6 or something, right? So this is typically the size of the grit which we consider, means the side of the sand. If you see that, no, I want to remove much more finer sand, you can, but it is not required. So these are the numbers. Actually, you don't have to play, but I'm just for learning purpose, I'm playing it. I just put 0.18. Then there are certain things Stokes law velocity is already calculated. You remember that formula, SS minus 1 d square, all this 1. Here is specific gravity of water. Okay. And G18, you know, d square, you know, mu, you know. Because of this formula, then you can calculate Reynolds number, complicated formula, but which is put here. And then also you have the Reynolds number for the transition flow. Vs is equal to so much. So this automatically comes. Don't expect me that I'm going to teach you all this. Okay, these numbers automatically come. Removal efficiency automatically come. Then you assume removal efficiency of the grid. Maybe I can put 85%. I do not 86%. And this one comes actual surface overflow rate. Okay, this will automatically come. Let's try to get into the number. So what it's saying here is two velocities. Horizontal velocity of flow VH is equal to peak discharge horizontal area. Yesterday I was in the slide now. So it says VH should be less than VC. Okay, VH should be less than VC. So we go and check VH and VC. Provide a depth of the weir. Critical displacement velocity is written here now. VC is how much? 0.161. Or horizontal velocity is VH. So VH is 0.6 and critical displacement velocity is 0.161. Right? VH should be lower than the VC. Right now, VC is 0.161 and VH is 0.09. Your screen is perfectly designed. Now, you have to do that. Assume the width channel for the grid. Now, I'm just playing with it a little bit, 0.40. Okay, now you can see you are getting a problem, right? And if I just try to say 0.3, no, sir, this is absolutely wrong. Because here, the VC is lower and VH is higher. Okay. So this is what has to be learned here. VH less than VC. Which one is the design is correct design? So design is VH should be lower than VC because that is the purpose here, right? It is absolutely reverse of the inflow chamber. In inflow chamber, you were not looking for any sedimentation, but here you are looking for sedimentation of grit. If grit is replaced from there because of higher velocity, then what is the purpose of putting grit chamber? So this, you want stilling here. You want things to slow down. You want the grit to settle here. And for grit to settle, you will put this number as 0.4. And okay, this is acceptable, but much acceptable number is. So we'll provide a grit removal unit of 3.4 meter length by 0.5 meter width with 0.3 meter side water depth and 0.3 meter of free go. One working, one standby. And then one area in the grid. Why this difference is kept? Because understand, when the grid settles, then the bottom, the layer keeps on growing. When the layer keeps on growing, same amount of water has to pass, right? So it will start disturbing the grid. So as the grid keeps on filling, right, the gap between VH and VS reduces. And gap between VH and VC will reduce. So therefore, it is better to go for 0.6 so that you have sufficient gap between VC and VH. This will make sure that at least your grit removal system will last for 4 or 5 days. Maybe once in a week cleaning you have to do. Okay. So provide the dimension of the grit chamber as something like this, 2.9 meter by 0.6 meter, and go on. Now, I'm not in a mood to actually go through the entire file, but this file is available with you. How do you size equalization tank is provided here. So you can say the provided dimension of the tank has this much. Then what kind of mixing arrangement you require? So some people say, assume 5% BOD removal in this tank and size everything. What my point? This is what is the assume 5% BOD reduction in the tank. That means whatever total area you calculate, at least 5% you will put into mixing. Okay, this is the way it is done, you know, in books. But otherwise, if I'll go, I'll teach you that air mixing criteria I told you not yesterday. that 0.3 to 0.4 cubic meter per cubic meter of the aeration tank volume should be the air, right? To keep it non-septic. Otherwise, if you follow this criteria, nobody is going to object to your design. So just put it 5% here, nil to 15%. So just 5% here. And incoming BOD from sewage automatically, BOD is to be reduced is 11, BOD load is 15.4, oxygen requirement 2. All this calculation will go. Oxygen requirement is 30.8, and therefore your cage actual air is around 90 cubic meter. So let's imagine 90 cubic meter air is coming into the system. Then what you require is raw sewage pumps. I go further down. You require aeration tank. In aeration tank, you require one aeration tank. This is complete mixed design. Your cubic meter flow rate, you know that. BOD level, you know that. MLSS, now how much you want to keep. F by M ratio, how much you want to keep. Same style, the way it was there in the CPHU manual. Hydraulic detention time. Okay. This is calculated automatically when you these two numbers you put. What is missing here? The design does not talk about SRT. So this design is typically applicable when you want to do a little bit of crude designing. Do not want to check SRT, because SRT is the term which actually relates to the treated water quality. So are you able to predict a treated water quality from this kind of design? The answer is no. But in terms of the dimensioning of the plant, you can say, okay, for this particular design, you provide this dimension time. Now, if I have to quickly go back and check what was the Excel I previously did and what is this Excel, so I'm just going to make a little changes here. You might say, Sanjeev, you are very fast. We cannot do that fast, but it's okay. Don't worry about it. There's a lot of things which are hidden, which I have to unhide first. When I unhide, how much I was talking about there? 1.1 MLD, right? 1.1 MLD was something I was talking about. Now I'll hide everything. Okay, and I was talking about the BOD of around 238 or something, 240. And how much MLSS I was talking about, if I remember correctly, if anybody can remind me, I remember that. It was 3000 and 0.3. Okay, and for the time being, I presume there is no BOD removed here. So it is 0.1. Never type 0 in an Excel. Otherwise, formulas will go here and there. Type a very small number, 0.1, maybe 0.01, whatever it is. Never type 0. Otherwise, it will start showing division 0 somewhere and you will struggle what has happened. So typically, it is showing me a 66 cubic meter tank. Something similar it was showing there in 355. Now, this sheet says if you have a liquid depth of 5.2, then you can design a 8.2 meter by 8.2 meter by 0.5 meter flow tank. Right? Then, but when you come here in terms of blower capacity, you come say BOD load, then this, then oxygen requirement for 1 kg of BOD removal. Okay. Now here it is put as 2. Ignore table above, as the air requirement is often governed by mixing and not just oxygenation. Remember why this line, because that's the previous sheet I explained it to you, right? When I was explaining in the table, it is written 0.1 to 1. Okay, but sometimes that may not give you enough air. That sheet once designed, that time, whatever knowledge was there, and I always believe that, people keep on believing in lots of copy paste. So that sheet is probably only valid for surface aeration, not for the mixing criteria. Over a period of mixing criteria has been changed, but people have not decided to change it. Who will change it? Ultimately, engineers like us will change. So they are not changing, no worries. You remember this knowledge, you put somewhere close to around 2 here. And if you put 2 here, you have the air requirement of 1039 cubic meter per hour. If you have a fine bubble diffuser, which can give, again, check with the vendor what you wish to install. For example, HD340, a diffuser coming from a very good company called Jaeger, which is a German company, gives 7 cubic meter air. So you require 149 such diffusers. Your aeration tank is designed. This is the way. Now there's so many other. You can see alpha, Ke, K theta, and it says MCRT calculated is coming as 4.57, which should be 10 to 25 days. So all these calculations are still there in this particular format. You can keep on going. I'm sorry, I'll go a little bit faster because I have to cover one or two more important Excels. So this is the secondary clarifier. Now, do you want to design secondary clarifier here? The answer is no. You already designed HRSCR. You know how to design it. But on the same basis, if you have to put something like SOR, what is SOR? Again, same thing. It is written here: 8 to 15 average flow and 25 to 35 for peak flow and extended aeration. Is given the criteria: a cubic meter per square meter per day. Now, if you divide by 24, it becomes per hour. So there in the primary clarifier, I was talking about 1.8. So what is this 1.8? Now it is 15. 15 divided by 24. We are talking about only 0.6. Okay, in secondary aeration. Side water depth again is given as 3.5, usually 3.2 to 4.5 for extended aeration. For simple plant, you can even go for 3. Okay, so these are something which will be able to put this number. Again, here the same thing will come. Provide a 9.7 meter diameter, 3.5 meter side depth, and 5.5 meter flow. Do you have a flocculator inside it? The answer is no. There's no flocculator in this. But do you have a central well inside it? The answer is yes. So you will provide a central well here, which is not calculated here. Okay, it's just a calculated diameter, but there will be a central, cylinder in which the influent will come. Then so on and so forth. You can calculate return activated sludge flow, then treated sludge pump, then even pressure sand filters, and maybe filter feed press, and so on and so forth. This is a large file. You can keep on going there. And finally, you will be able to put some hydraulic calculation. If average ground level is 0, you will be getting all these levels. Don't worry about it. Somewhere it is shown right now, minus 1.89. Don't worry. Give it to the hydraulic designer. He will understand how to make the HFD of this particular plant. It's a very nice Excel. I love this Excel. But if I have to say that this Excel, will you understand the first day you use it? The answer is no. You would have to do it, take a piece of paper, write it a little bit, churn your mind, and just I'll click nearby. Okay. The same thing you can design for very conventional STP. Right now, we were working on the extended aeration file. Okay, and just nearby is a conventional aeration file. Same, something very, very similar, but with some differentiation. So you will get everything hydraulic. So all these things, what we are talking about, for example, bed level of the treated sewage sum will come somewhere 5.29 negative. Now, if you don't want to go up to like this, then you will have to say that average ground level, whatever 0, 0 you are putting it, water level in the inlet chamber be 2 meter. Now, you do not want that. You are saying that it is other way around. So it is other way around is this is the number which is entered 0. This is the number which is coming as entered as 2. This is the number which is entered is equal to 0.6, right? These are the numbers which are entered, but these are the numbers which are coming automatically. So which number to enter and which number is to, so for example, your water level itself is coming at negative 0.3, right? Okay, and you want to provide a liquid that at the inlet of the chamber of something like maybe only 0.1 or 0.5. You can see everything is going negative, right? And it is okay. This is what the plant hydraulics says. This is the way you will design the plant. Unless you decide there will be a sump and I'll pump it and take everything up. Got my point? When you decide I'll take a sump, I'll take a pump and take everything up. Otherwise, everything will show as negative. It going to 7.9 negative. So I am closing this file. Just relax a minute. I know today's session could have been a little heavier for some, which I'll get to know during the question answer session, but it was important. See, you guys have spent 4 days. You're planning to spend 4 days with me. In 4 days, I do not have to really teach you thumb rules. We have to tell you what it is, which are the right tools, which are the right files. So you may not use it, but there may be some juniors in your company. Give it to them, ask them to learn. And one fine day, everybody will start using tools and doing a proper design. And even if somebody says, what is thumb rule? From where the thumb rule comes? The thumb rule comes with experience. Like if it is very practical. If you ask me, Sanjeev, what you do when you work with a design like somebody says 100 kiloliters per day STP, I want to put what you want to do. So I'll go on a calculator, and whatever this is done in Excel, I'll quickly do in my mind, and I'll say, sir, take a tank of 8 meter by 8 meter, and I think 3 meter diameter clarifier should be enough for you. But that is not thumb rule here. That is experience. Got my point. So we don't get confused, because I have a project which I already done, so I remember each and everything. Somebody else says me, sir, I want a 25 meter cube per hour RO plant. How much it will cost? I can immediately say 32 lakh rupees. Is it a thumb rule? No, it is experience that the previous project which I have executed costed me this much, so maybe I add 10 more percent and give it to the gentleman. But this is not to be taught to the next generation. What you have to learn is the right way to design. I hope my speed is okay. And there's so many files right now available with you. So what I'm going to do is not to go through the files, each and every file for maybe 15-20 minutes, but I'll go through the curtain raiser of these particular files, explaining you what is the importance. For example, tube settler. So when you go to this particular size file, now you will be able to do a dimensioning of a tube settler plant, complete tube settler plant. There will be some things which has to be a little bit understood. What is the settling area per meter cube of a media? This data will come from suppliers like KPAC, Muntars, and whatever it is. Somebody says mine is 9, then press 9. Somebody says mine is 12, then press 12. And then enjoy the sheet. No, you cannot just think that whatever is written by Sanjeev is fine. So I'll cross this file. So this is just file we can use for tube settler. As such, I told you not to use tube settler in STP. Remember that. Then we go to, maybe right now I'm going to this file called SBR design. It looks a neat file, so you will enjoy this file. So before you start trying to use tools, see, sewage treatment plant telling one thing, informing one thing, information what is the business is one thing that I've done in 2 days. Then we come to designs. So a designer must understand few basic terms. So this is a terms called yield. What is yield means? It's a yield of biomass. Yesterday when I was talking about now, COD becomes cell. COD becomes cell means yield. So there are some formulas given here. You have to read yourself to understand what is aerobic biological reaction. For example, C6H12O6 plus 8 oxygen, little bit of ammonia available. Can you understand? I said 100 carbon, 5 ammonia, 1 phosphorus makes the basic cell called C5H7NO2. For a bigger cell, P also is required. For a much bigger cell, even some metals are required, some calcium is required. So let's not write those formula. C5H7NO2 synthesis is bolte hain. So we use a term called substrate. What is the substrate in this case? Glucose. Glucose is actually a COD, which has become a particulate. A substrate has become particulate. Again, I'll repeat, substrate has become particulate. So what is the yield? 0.42 grams cell per gram of glucose use. Now, over a period of time, people use thumb rule. Sir, how much is the yield? I'll say, okay, 0.38 per kg of COD. Every kilogram of COD consumed, you will get 0.38 kilograms of biomass. So, but is that thumb rule? No, it's experience. Okay, this is what happens. If we use COD and VSS, then we can calculate the COD of the glucose, you can calculate the yield, you can calculate the COD of the cell tissue, you can calculate. So what you will find is we are talking about something, this much gram of oxygen has been consumed by 1.42 per gram of cell, which is destructed. So what is COD utilized is equal to COD in the cells plus COD required in the oxidized substrates. Cell COD, cell also need to be destructed. So There are so many small things which are written here. Something similar, you will find it written here. Then we come to a table called this. Now I'll slightly increase the table and I try to just put a significance of a little bit these things. Mu m means gram of VSS per gram of VSS per day, right? Ks, yield, depth, FD, theta C, mu m again, small kd, small ks, and these are some range and these are typical number. You'll say, sir, from where all these have come? All these have come from microbiology chapter in McCaffrey and AD. You would have to understand a little bit of this. When you understand a little bit of this only, then you are able to understand the biological formula, because I understand here what is happening is here there is a mixture of two chemistries. Which chemistry? Glucose is a chemistry, right? But cell is a microbiology. So here the formulas are slightly complicated. Here a substrate become a cell, and cell is a particulate. That particulate again hydrolyzes, dies, and again gets converted into gas. So in terms of chemical engineering, you may be one of the best chemical engineers, but you may be having difficulty in understanding it. When you will understand it, when you understand it, when you understand a little bit of it. So these numbers are important. Don't get afraid of this. So the way we have activated sludge kinetic coefficients for heterotrophic bacteria, similarly we also have for autotrophic bacteria. Because if you don't do, then you cannot design well. Now let us click on the SBR design. I have only 4 minutes left to tell you SBR design because there are so many other designs possible. So what we'll do here, we will just simply try to explain few things. Flow rate, everybody understand flow rate, temperature. Then we have to enter BOD. But BOD, my bugs don't understand. They understand SPOD, soluble, right now. COD, again, bugs don't understand COD. They understand FCOD. RBCOD, they understand very well. Why? Because this is something, is a love food. It will going to come to me. TSS we understand, total suspended solid. But what about VSS? VSS means out of those total suspended solids, which one are volatile or organic in nature? Because bugs cannot eat clay. If you put clay, calcium carbonates, will the bugs eat? The answer is no. But the bugs can eat a leaf. Bug can eat a skin. Bug can eat the pulp of mango, provided it hydrolyzes. So what is important for me is YSS. Similarly, TKN is important for me. Ammonium nitrogen is important for me. TP is important for me. TN is not important for me because TN will come into calculation only when I am going for a design of anoxic reactor. And of course, alkalinity is important to me because in the class day 1 I said pH is equal to 6.3 log of bicarbonate divided by CO2. So alkalinity tells you the role of CO2 and pH. Sorry, I'm drinking water. 1 second. Then when you go inside this particular file, it will say the treated effluent quality. You need to really tell something. So for example, I want to do nitrification at such a level that 25 ammonia becomes 0.5. Got my point? There's some number which I have to predict. So right now I'm putting 2. Then it says step 1, calculate BCOD, BPCOD, PCOD, NBVSS and ITSS. All these numbers you need not calculate because if you fill these numbers, these are automatically calculated. You don't worry about it. The green cells just are for information. Some formulas are given here, how they come. Step 2 is that you have to select some design conditions which will come from experience, your engineering capability, your know-how, etc. So typically any SBR plant is designed with 2 reactors, large one. But you say, sir, I have only 1 plant. So design with 1 reactor. I do not mind. No problem. Just put 1 reactor. But in 1 reactor, such a high flow rate, I won't recommend. So maybe you want to design only a 100 KLD SBR. Let's put it. Very simple. For a school, for a hospital, 100 kilogram meter cube per day reactor you want. And you do not have all these numbers, so let my number remain the governing numbers. Okay, they will not be bad numbers. So, or if you have some numbers, you put it. So this is what we will put. One number. This liquid depth we don't change. It can be 4 to 7 meters. I have given a hint here. Decantation depth, we keep it whatever you don't know, just leave it there. SVI parameters that control sludge settling 150i. This is interesting. NOx as percentage of TKN. See, total Zildal nitrogen, how much NOx conversion is possible. So if you do not know, let it remain 80. Maybe I'll keep 67. Maybe I can keep 70. You say, when you say maybe I can keep 70, what is 60? How it is coming? The answer is even I don't know. We have to read a lot of microbiological equation and chapters again and again to get this number to understand even this word NOx as a percentage of TKN. Out of the total Zildar nitrogen, how much nitrogen has got the potential to become NOx, NO2 or NO3? Okay. Then reactor MLS is something which will fail. So, okay, I asked my colleagues. So somebody says 3200 is the right number. Then we have to adopt a SBR cycle. And this SBR cycle, we have choice to adopt whatever we want to. So right now it is filled as 3, 2, 0.5, 0.50, and 6 hours. You want to change this? I do not mind. Okay, let's change it to 2. So it becomes 5. Now 5 is not a good idea. So you may say, this, let us make 2.5. That also is not a good idea because 5.5. So you say, okay, let us do this 0.45 and let us, this is 4.45. See, human beings, we want to change something. So no, still what is happening is, no, it is 0.75 and 0.75. So we again get a 6-hour cycle. That means number of cycles per tank per day are 4. And number of cycles per day itself are also 4. So fill volume per cycle is how much? Only 25. So at one point of time, you can only fill 25 cubic meter water. The next step is very interesting, which is determine fill fraction per cycle, VF by VT allowed, and compare it to cell number D28. So D28 is somewhere where I've written decantation depth is 30. See, decant depth is only 30. That means 70% of reactor remains fill. Only in the top 30% reactor, always the new water comes, treated water goes out. New water comes, treated water goes out. So 70% of the tank remains always filled. Okay. We go further down and we check here. It says 0.426. So change your volume should be greater than cell D28 in fraction. So how much it is coming? 0.42. How much I've taken? 30. So even I have gunjaish, I have margin. I can go up to 36 here. Let me see what happens. Okay, 36 here. Let me be very comfortable right now. Let me go up to 40. Okay. So it is still 0.424. So I do not have a problem. But can I have a decantation depth of 15? So the answer is no. You should not. Right? So this formula suggests my maximum decantation depth, which I'm possibly trying to do, could be 0.42. All this has got some significance. So right now I'll put for your comfort, where is that gone? 28, 28. Okay. Yeah. At 42, no problem, 0.425. Okay. We move it further. Then what is do? Determine overall hydraulic detention time, which is required. So there's a decantation depth, which automatically comes 2.52 meter if the reactor is 6 meter tall. Okay. This is where I have filled certain things. Because of this has been calculated automatically. Pht is calculated automatically, and overall retention comes as 14, which is okay. This is hydraulic retention time, 14.28 hours. Should be between 15 to 40. So, am I meeting this criteria? The answer is no. How do I correct it? I go up and correct it. This 48, you make it 40. I think this would be corrected. Can you see it? We are just on the border, 50. Similarly, I'm sorry, I'll not teach you here onwards everything. There's something called PXTSS SRT. What it's saying is, I'll explain what this says. It says, if you want your particulate, right, to be converted to substrate, how much minimum sludge retention time you want. Right? It is not that your all the particulate will become substrates. And particulate have VSS. It's an organic content. And S0 to start with is only 352. Okay, substrate at zero condition. Substrate means something which the bugs will eat. Y is yield. KD is depth, right? So all these things, formulas, na, step number 6, I completely eliminate. Please read a little bit yourself to understand and come to a level where what I'm saying is you have to feed a number here and check this. You feed a number here and this difference should become 0, 0. Just feed a number here. So maybe I feed a number called 22. What I say, it is going towards more negative direction. If I put a number called 16, okay, it is coming as negative direction. If I keep it a 15, and it is coming again a negative. If I just put 10, it has gone towards positive. So there is some number authority, which is approximately, see, these are biological calculations. So they will have to balance it out by growth and death. Growth means what? Again, understand. Growth means substrate is becoming cell. Death means was the cell is already killed. Now the cell has to be again hydrolyzing, right? Because substrate is still where? It is still in the, sorry, particulate is where? It is still in the reactor. So these two equation where the growth and death is taking place together must be balanced for some SRT. Typically, I just press 13. So we are in problem. We press 12. We are in problem. We press 11. We are in problem. Oh, first time slightly positive, right? So maybe 11.1. And we can leave it here. Maybe 11.2 or 3. We can leave it here. The moment we are very close, 11.1, 11.2, just leave it because it doesn't matter. It's a mathematical model for designing of your system. So positive 300, it's okay. Just don't try to make it 0, 0. Otherwise, you will, it will look very funny. Can I put an auto iteration there? The answer is yes. One fine day I'll put it. I am yet to really figure out how to put it. One fine day I will put automatically iteration. But if I put an auto iteration here, the entire glamour for the entire 6 formula will go. Just hide it there. Then it is of no use. Then when you proceed and then you talk about something called step 7 is to determine MLVSS concentration. Leave this step. Determine this ammonia oxidation to nitrate. Can you understand? Ammonia oxidation to, because in SBR reactor I'm oxidizing ammonia. I'm going towards nitrate, right? So all this complicated formula will start. Leave it, leave it, leave it, leave it, leave it. Keep going down, down, down. So typically 145 different steps have to be performed. But do you have to perform these steps? No. 1 or 2 times, just go through this particular file. You will be able to take a SBR summary like this automatically from this file. So I have not gone into this file detail, but what I know is this design is just print it, it will work. 100, 22, it says fill time, react time, total aeration time, settle time, decantation time, cycle time, total SRT 17, right? Tank volume XFB 63, fill volume 25, fill volume, tank volume ratio 0.4, everything, MLSS, MLVSS. Now you can see MLSS 3200 and MLVSS 3781. Is it possible? No, because I have not yet completed the design. I have to take time to complete this design. Okay, so this kind of output number, but you have to follow those numbers. You keep on going down in this particular file systematically. Your thing will explain. So there would be certain things called you check this, you check that. That much you can follow. So with this, I close this particular file right now. I save it as it is. And today's session, I will go through one more file, which is the last file today. There could be anaerobic USB. I am not going to get into that, but you keep this file with you. I'll give you a activated sludge process design. This file, very interesting file for C removal and removal and also denitrification. That means anoxic tank reactor. And if you click this particular file, you will have to go through the something very, very similar. Same here, activated sludge coefficients put here, nitrification put here, designer input with respect to oxygen transfer efficiency, liquid depth, point of air release, how above, DO, site elevation, pressure, alpha for C, alpha for N also. Now, nitrification karna, you have to do nitrification. So alpha value for nitrification. Aeration beta for C and N. So all these numbers you say, no, sir, I don't want to understand this number. You please design my plant. It doesn't happen because it's a biokinetics. It's a microbiology involved into it. Then you have to have a feed effluent area. Then you have to have a treated effluent area. You put everything here. When you put this sheet properly, you have to fix certain numbers here. C20, CT, M, R, Y. What is R? We all remember R. 8314. Gas constant. Remember? So why it is important? It is important because how much air I am giving, what is DO, all these numbers are very, very important to understand because it's a combination of 2-3 sciences, physics, chemistry, and microbiology, which is the life science. So when you go to the design file, now this design file also is fairly straight. You keep on following step 1, step 2, design suspended growth system for BOD removal only. So calculate px VSS above value. Then next line, determine the mass of VSS. Then calculate the mass of VSS. Then select a design MLSS mass concentration and determine the aeration time, volume, and detention time based on that. So this step by step follow. Determine F by M and BOD volumetric loading rate. So similarly, 5, 6, 7, 8, I keep on going down, 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 down. You follow 30 steps. And when you follow 30 steps, you will get a design summary in this particular file as this. So if you want to do C removal with nitrification, then follow column E. But if you want to follow C and N removal along with denitrification both, then you follow this. And what it exactly saying is that you require MLSS of 4,000, you require tank volume of 1131, out of which 113 is the volume which will be required along with DN. So all these kind of calculations are possible. Oxygen required is only 69 kilogram per hour. But if you now, whether it is calculating the airflow, yes, it is also calculating the airflow quickly, right, from the design file. So you require less air if you are having a denitrification. Why? Because nitrate provides that oxygen. Some people will ask me, sir, if the nitrate is providing oxygen, can I reduce air? The answer is yes. You see, it is already there in this property. What is the RAS ratio? What is the RAS ratio? Come here is something number called 4. Now, I'm not saying you always maintain 4, but this particular file right now is showing is this will be able to calculate to you how much exactly the written activated sludge has to come to the anoxic tank. So I was telling in the theory that it could be anything between 1 to 10. Now, it depends upon what is the nitrogen level you are feeding. This is a simple kinetics. If you fill the number, it will calculate and give it to you. But whether you want to use it or not, then experience comes into the picture. So typically, we do not recirculate more than 4 times for a smaller plant. And for larger plant, not more than 3 times. But theoretically, you can recirculate 10 times also. Okay, 12 times also. It depends what is the final nitrate level you are looking for. For example, I'm not able to interact with you, but some of the one of the tender I was working, the initial nitrate level was 25. Nitrate, NO3. I'm not about ammonium nitrogen. I'm not about Zeldal nitrogen, and the river water nitrate also, could be sometimes 6, 7, 8. Now, if you say no, your treated water TN should be less than 5. So what the hell we are talking about? We are talking about taking the water from the river and converting nitrate to N2. It is practically a rubbish thing. But if the tender is like that, then you are in problem. Because right to start with inorganic nitrate itself is 25. And you want in a treated water guarantee total nitrogen less than 5. That means even the inorganic nitrate which is available to me in the water, you are expecting my bugs to do that job. So it will not happen. So certain times, certain things which are written in the book or written in the tender documents are not the right thing. And you can argue with the buyers or designers only when you have little bit of more knowledge about this subject. It is not very difficult. A young engineer, if he reads 6 to 7 hours a day for a period of a month or so, a book called Pfd, you will understand all this. But if you don't read it right now in your career and you delay it for 15 more years, you'll never understand this. Because this is somebody else's subject. We have not been taught this subject. I've completed my engineering from IIT. I have not been taught this wastewater engineering with the microbiology perspective. Thumb rule perspective, okay, you take this much, that CPHU manual, you take HRT this, you take SRT this, you take aeration tank, put everything in one place, it will work. And it works. But if you have to understand the design, that is okay till sewage treatment plant. But if you want to become an effluent treatment plant designer, it's absolutely impossible. With this, I come to end of this today's session. I will just tell you the file. Aerobic USB, you will be able to design USB. Sand and carbon filter design, you will be able to design sand and carbon filter. UF design, you will be able to design UF filters. API sizing, you can design API. Lime softening, you can do lime softening. Please believe me, this Excel is beautiful. Ion exchange softener, you can do the softener designing. Some tanks you want to design, you can do. And finally, this is the one sheet which I'll click for you. If you are if you're not a designer, and if you're looking for, sir, I am the person who is responsible for my plant, and how do I monitor the data? So this Excel provides you a nice glimpse. How do you have to actually design your MIS? Put equalization tank, go for your key data. If your key data is changing, you please change it. pH, COD, BOD, ONG, TSS, TDS, etc. You see, it's no ammonia here, no NS3 here, right? If we DAF out, then buffer tank, then USB, then tube settler. After USB, I accept tube settler. Understand, because it's a roughing. There's a lot of work to be done. Aeration tank. After aeration tank, you can take aeration tank. If MBR, different parameter. Aeration tank, simple, then different parameter. Got my point? If MBR is there, then you have a different Excel log sheet. Then you go to clarifier. Then you go to talk about your MBRs. Flow in, flow out, TMP, flow return, percentage MLSS increase, arrow, right? What is the percentage MLS? All these parameters. You maintain this plant log sheet, and you don't have to maintain date-wise date. You also put the design number, right? You also put the expected number, and then you put the actual number. And then finally, whatever is your data, you find out average, you find out minimum, you find out maximum, okay? And then you can hide all this. And then send this Excel sheet to me. You said, my plant is behaving like this. What kind of suggestion you can give? Then you will be able to give the suggestions. But if you do not do the data logging of your plant itself and just say, sir, in my aeration tank, there is some smell, what can I do? The answer is, God bless you. Because there is no data available on the plant performances. And especially I designed this sheet for an MBR customer once. That he said, I bought an MBR and all that. Sir, I said, you bought an MBR, but please buy a computer also. Put Excel into it and put some data. So he started laughing at me. I said, yeah, buying an MBR is fine, but I have buy a laptop and give it to somebody. Let him feed the data. He doesn't feed the data. I cannot say I'll help him. Okay. So anyway, that was not a joke, but it was a reality. It's 6 o'clock today. I am sure you must be tired today. Because going through theory, at least you see some pictures, you see bugs, you see some photographs, so 3 hours. So you should not thank me today, none of you. I will thank you that you listened to me for 3 hours. But I wanted 40, 30 odd people who are listening to me to listen to me and understand the importance of these XLS tools. Today, I did not talk any theory because these are the tools of the engineers. These are the tools for the designers. Learn it, refine it, improve it. You may find some mistake somewhere. Come back to me and I'll help you throughout my life. Okay.